we have the pleasure to have Thibault. Lagache he did his PhD under my supervision a couple of years ago, and then he moved to Pasteur Institute to work on image processing, image analysis, and statistics. And then he moved to Columbia University to work on computational modeling of neuronal networks, but also on dendritic spine. So we are very happy to have him here today, and he got just recently a position at the Pasteur Institute. Thank you, Thibault.
Thank you. Thank you for the introduction. So today, yes, I present a work I did at Columbia with Krishna Jayant and under the supervision of Raphael Juste. So Juste's lab is an experimental lab, and so I have access to data and for all these models. So first of all, I wanted to recall why it is important finally to analyze the dendritic spines and how the dendritic spines respond to a signal. Because actually, one neuron here, so you have an axon that can generate an action potential if the arriving signal reaches a given threshold. And this threshold will be determined by the integration of tens to hundreds synaptic connections that the dendrite is making with different other neurons. And so it is, and each excitatory PSP, actually most of them arrive at these dendritic spines, which are located. So here this is a small picture. So on this dendritic tree, you have a lot of dendritic spines. And so each of these dendritic spines is one connection, and then you have to integrate all these hundreds of connections to generate or not an action potential. And because this is a thresholded process, it's non-linear, so a small variation in the response of some individual spines can or not generate an action potential and send some information after. And most importantly, all of these dendritic spines have many, many different shapes. So most of the time we concentrate on mushroom shapes with long nape and some bulbous head. And also these shapes change dynamically over time. And interestingly, they also change with activity. And so people made the hypothesis that finally the shape might encode the memory, in the sense that depending on the activity that the dendritic spine has received, he might adapt his shape to be more or less efficient. Efficient in the sense that he can more or less transmit the arriving information. And also, I don't show it here, but in some neurological disease, such as the Fragile X syndrome, you can have a dramatic change of shapes of these dendritic spines that can appear much longer. What does this disease do? You're more stupid, essentially. Yeah.
Sorry.
No, but yeah, the Fragile X syndrome is that when you can see it's like the idiot of the village. So it's,
because nobody understands you, not because you're stupid.
No, but it yes, it impairs the proper function of your brain. So typically the question I ask is how the shape can influence the response of the spine to one input. So you have an input that arrives, and how the shapes is going to influence the transfer function of the spine. So there are many other determinants that can be molecules, channels, actually essentially, but here we really concentrate on shapes. So it is known now, I think it is well recognized now for years that these shapes is actually a good restriction to diffusion and compartmentalize some signals such as calcium, or here this is some FRAP experiment where you look at the diffusion from dendrite to spine or spine to dendrites with FRAP and with recovery time, and you see that you have like time of the orders of hundreds of milliseconds, and depending on the shape of the spine, so typically these long neck spines lead to a much longer recovery time compared to shorter spines. And actually a lot of work has been done by David and Zev Schuss, essentially, plus postdocs and students, to derive, I think this is one of the last complete expression of the escape time from this head to the dendrite. And so as David showed yesterday, there are three terms. So these terms, this is the mean first passage time of one ion to the entry of the neck. This is the mean first passage time to travel through the neck. And this time actually, in most of the geometries, can be, in most common geometries, is dominant. This is the time because the particles can go up, can go and return an infinite number of times between the head and the neck. But for sure, all of these terms, for example, these terms, David made a lot of new development depending on the geometry of the junction. This term, you can argue that, for example, if you have some potential barrier that prevents the ion to return from the neck to the head, this term could drop. So it's still something that is under study and under debate. But what is important is that when you plug typical parameters in this formula, and actually, so you can reproduce this type of formula, but what is important is that the escape time here with pure diffusion is of the order of 102 seconds. And so it's long. It's long compared to the time scale of synaptic transmission. As we have seen during all the week, I don't know, release of fusion of vesicles is like 100 of microseconds. Opening and closure of channel is of the order of, so actually this is the same order of magnitude. But typically electrical signals are more of the orders of 100 of microseconds or very few milliseconds. So here there was something that that puzzled me, because usually when you consider the transmission of an electrical signal in a dendritic spine, you consider that this is due to the motion of ions. And if the motion of ions is dominated by some diffusion, then you have a problem, because the time scale of diffusion is much longer than the time scale of finally synaptic transmission. And actually the electrical filtering of a dendritic spine is much more controversial. So this is a paper of Eustace's lab like 10 years ago, where they looked at, so they did some glutamate encaging at different sites along the dendrites for different spines, and they can observe a decrease, a filtering of potential that is increased when the dendritic spine is longer, making the hypothesis that the neck length is filtering the arriving electrical signal. So the longer the neck, the smaller the response. Meaning that at some point long spines would be isolated from the dendrite. But so this is one study, but actually if you read the literature, you have more or less half of the labs that I say that there is no clear electrical role of the spine, and half of the labs that are completely convinced that there is a strong role of the spine in filtering the electrical signal. So typically, actually I didn't put where these images are coming from, because this is much to illustrate that there is a true controversy. So this paper shows that actually, yes, the neck resistance is high, and you obtain neck resistance of like almost a gigaohm. A gigaohm, so like 600 mega ohms. And here in this paper, they say, oh no, the neck resistance is more or less around 30 to 40 mega ohms. So there is a big discrepancy because between the values that you can find in the literature. And the reason is that actually these spines are really tiny. So first of all, it's really hard to make a direct measurement of what exactly happens in these spines. And actually, in Houston Labs, they did, I think, almost the first direct measurements of voltage inside the spine using nanoelectrodes. So this type of measure, this is the type I use in my modeling, but there are very few. They measured it in like 4 to 5 spines, not more, because this is a really tricky experiment. And so voltage imaging is developing, but right now it's still very noisy and slow. So you have a slow change of conformation of the dye that is used to image the voltage, making the deconvolution very difficult. And this is the last paper of Jérôme and David that try to deconvolve the signal, but there is still controversy because especially in dendritic spines, the change in fluorescence is going to be very small. And actually, depending on the deconvolution method you're going to use or the dye you're going to use to measure your voltage, you're going to obtain very different information. And also, people actually are using different experimental conditions, different animals, and different type of experiment in vivo, in vitro, in slice, at different ages. So it's really hard to compare. So typically, if I don't make a mistake, I think that dendritic spines in vitro are smaller than dendritic spines in vivo. But I'm not even sure. So, but there is a difference of shapes between the different experimental conditions. And so our goal was to develop a robust theoretical framework to interpret all of this data.
Thibault, what did you mean about the difference between the spines in vivo and in vitro? You said something.
Yes,
what exactly
actually
is
when I say in vitro, this is culture, in culture.
Yes.
And so,
are the spines bigger, smaller?
So I think
what's different? Yeah.
Yes, actually, I think that in vitro they are smaller, but
okay,
I mean,
no, that's
specialists could confirm. But there is a difference because they have not. I mean,
yeah, it's a difference.
I mean, it's not the same conditions, the same.
I can comment that there is a paper from Thomas Oertner on organotypic slices. So as long as you have a kind of long-term culture of these slices, then you have a very heterogeneous neck conductance or neck resistance. And then in acute slices, you have very low neck resistance. There seems to be a disorientation or a depolymerization of actin that plays a very big role in this kind of resistance on and off. Right. And if you have a slice culture, or I think also in vivo, you have much more heterogeneity in this kind of parameter than in these acute slices. That's much less.
Thanks. So actually, I told this to say that finally, when you read all these studies about the neck resistance and how one dendritic spine is going to filter the electrical signal, actually maybe everybody is true. But it really depends on what you want to see. And so our idea was really to develop a robust biophysical framework to interpret this data and, I mean, try to give an answer. So when you want to do some, to look at the electrical activity of neurons, what is usually done is to use the standard cable theory. This is a theory that is implemented in the big software neuron. And typically you consider that each part of your dendritic tree is a cylinder. So you have a big cylinder for the main, the apical dendrite. So this is the main dendrite. And then you have smaller cylinders for all the branch. And actually, people are also using cylinders for these dendritic spines. And so each cylinder, you have a longitudinal resistance due to the cytoplasm. You have some membrane, some capacitance for the membrane, some resistance for the membrane, which usually is really high. And then you can derive some ohmic law and some dynamics for the voltage propagation along your tree. So this theory is good. I mean, it has been introduced in, I think, 60s, like at the time of Huxley. It has been refined in 70s and 80s. And it works pretty well for large compartments, such as the giant axon that has been used at the time of Huxley. But actually, it makes a lot of hypotheses that do not hold in dendritic spines. So typically, it neglects every potential change in concentration, which is true for large compartments, but which is not for this femtoliter compartments such as dendritic spines. So here the spine head typically is more a ball than a cylinder, and it changes the analysis. And so, and actually it does not really couple the dynamics of ions and potential, especially when you account for this concentration change. And so this is some paper. So really one of the first paper that emphasized the importance of electrodiffusion in dendritic spine was from Terence Sejnowski, like almost 30 years ago. And this idea has been mostly reintroduced by David and Rafa Yuste in this perspective 3 years ago, and also this perspective by Rusakov and Mumingpu and Savchenko 1 year ago. And so we now try to reintroduce the idea that electrodiffusion is important, the concentration is important, and might change what we know about dendritic spine activity. So let me introduce you what we call electrodiffusion model. So an electrodiffusion model is two equations. There is an equation which is a Poisson equation. So the Poisson equation just relates how your potential is related to the difference of concentration between positive and negative charge. So this is the first equation. So typically it links the potential to ion concentration. And then your ions are going to move in the medium with diffusion and an electric field that is created by the potential, and the potential is created by the difference of concentration. So this system of equation is coupled, and it's really hard to analyze. And actually, there is no analytical solution except in 1D system or really constrained system. So typically what people do is that they're doing like some simulation, as Jérôme showed you on Monday. So typically you can use like a 3D COMSOL simulation to explore these different parameters. And but the goal here was finally to try to simplify the system by making some hypotheses to derive some coarse-grained system of equation, like a pen and paper's equation that give some insight on what's happening, and especially what is the different dynamics of the phenomena that happen during when a synaptic potential arrives. So just because many people in the audience are coming from different backgrounds, I just wanted to recall the main ingredients of the asymptotic analysis we performed to coarse-grain this equation. And so this is a typical asymptotic analysis based on perturbation analysis. So the idea of perturbation analysis is to rewrite the system of equation in dimensionless variables. And if you're lucky, you make appear very small terms. And then you can develop, like a Taylor expansion, the solution of your differential equation based on this term. And so here we just stop at the first term, like but then you can pursue development at 2, 3 terms to refine the precision of your solution. And a last step, because this expansion, usually when you expand your solution, you do not respect the boundary condition, and then the last step is just to match your development with the boundary conditions. And if you're interested, I encourage you to read this the PhD thesis of Gillespie under the supervision of Bob Eisenberg, where he gave a good introduction to all these methods. So I'm just going to show you what we did in the head with the Poisson equation. So these are the dimensionless variables. So typically you divide the distance to the center with the radius of the head. Or for example, for the potential, you divide by this constant, this gamma constant, which is more or less 25, the inverse of 25 millivolt. You divide your concentration by the bulk concentration. So here, there is an important hypothesis also, is that we consider that positive and negative charge are more or less at the same concentration and equally mobile, which is an important hypothesis of the model. So we can rewrite the Poisson equation, and we make appear this delta 1. And delta 1, actually, this is our small parameter. This is more or less, we will see later, but the Debye lengths, which with the parameter of the model are around 2 nanometers, compared to the radius of the spine head, which is more or less between 300 and 500 nanometers. So it's much smaller than 1. And now, typically, if delta 1 tends to 0, you see that locally you will have n equal to p, meaning that you have locally some electron neutrality in the bulk. And by reintroducing this electron neutrality in this equation, you obtain that your potential is harmonic in a ball. And here we used also the narrow escape theory, because neck radius is much smaller than the radius of the head, meaning that you can approximate the solution of this differential equation with the solution in a closed ball. And so in a closed ball, an harmonic equation in a closed ball gives you a constant solution, meaning that your potential only depends on time. Okay, so as I told you, I really stop at the first term, because then you can pursue the development.
A bit, what did you do exactly? So you insert n equals p, so then the Laplace is 0, so it cannot be the thing. So how did you get this solution? Phi of xt is 5.
This one?
Yeah.
So here, when you get some lapilation is almost equal to 0, so this gives you like
almost.
Almost.
Yeah. So what do you assume the first order? Okay. So what is the first order term?
Something that is proportional to this delta 1. It's small.
Maybe I have to look at your paper.
Yeah, I can give you supplementary information. I have not in mind the exact dependence, but the first term is small, meaning that you can have an harmonic potential. And actually, this almost constant potential is, I think, has been shown by Jürgen on Monday. So this is one of the figures of their paper where they did some 3D COMSOL simulation in a ball and with an absorbing neck. And you can see, so here they have a big drop of potential, but this is where they inject the current. But typically inside the ball you have something that is more or less constant, so except at the boundary layer, and you have a second boundary layer here at the entry of the neck. But so here I was talking about the bulk concentration, and in our model then we linked this constant potential to the boundary condition, because it does not respect the boundary condition. And so then you can expand locally the boundary, you can match this constant solution to the boundary condition with with some 1D analysis because you are very close to the boundary, so you can explain everything in one dimension, which is the normal to the surface. And so this result is well known in electrolyte physics. So typically, this potential will be this constant potential as a function of time, 1, and you have this term that that exponentially decrease as the radius is far from the membrane, and the typical length is the Debye length. And you have some, because here the concentration can vary compared to the initial C0 concentration, you have this additional term. But typically, what happens is that this is like the boundary Debye length. So everything is constant in the bulk, but when you are close to the membrane, you have a small increase of the potential here. Much of the increase is going through the membrane because the permittivity of the membrane is much lower than the cytoplasmic one. And for the concentration, so because you have an increase of the potential, you will have an increase of the positive concentration and a small decrease of negative concentration. So actually, the difference between positive and negative charge, so when you have an electrical potential in a ball like this electrical potential is coming from a difference between the total amount of positive and negative charge when you have positive and negative charge. And what happened is that everything is at equilibrium in the bulk, and this small difference between positive and negative charge is going to show up at the membrane, actually. And then, I mean, this is a simplified model because there is a lot of groups all over the world that look at these boundary layers because, for example, if you have a high concentration of ions, you can imagine that all these ions have maybe a diameter of few angstroms. But if you have 1,000 of small balls of few angstroms diameter, you can have some steric effects, for example. So it complicates a lot the analysis. But and so when you actually this relation is coming by the integration of the Poisson equation over the ball, and you obtain that finally this potential is more or less the potential of a capacitor. So as I told you, it's a very simplified analysis. But what is important here is that, and I think this is true in that case, with typical membrane capacitance and surface that you can observe, but again, these parameters might change in the spine because we have no access. Then a typical potential of 100, for example, 100 millivolt, which is very high. Typically, it's 20, 30 millivolt. Then the difference between the number of charge that you need to elevate your potential by 100 of millivolt is like 10,000, compared to the total number of charge in the head when you have like an equal concentration is much like 10 millions. So there are very few. And this is due to this very small capacitance. So a small change, so the important idea is that in this model, a small change of charge in the head can create large variation of potential. So when ions channels are going to open and some charge are going to flow in, the change of potential is going to be very fast.
So this is a relation that you obtained from the analysis of first order term, is that correct?
Yes.
Okay, so phi represents the potential in the head.
Yes.
And plus represents
the total number of positive charge.
In the head.
Yes.
And minus is the total number of negative charge in the head. So SHCM is a quantity that lives inside the bulk, because everything is inside the head. There's nothing here on the surface, it's in the bulk.
No, it's at the surface.
It's on the surface or in the bulk? Because on the surface there is the boundary layer.
Yes.
So phi is not necessarily constant. So because we had this question, and I think it's just a question of interpretation. What this can represent is something more related to what happened in the bulk. That is, there is what we have introduced with Jérôme, is that there could be what we can call a bulk capacitance that connect number of charge to the potential. But maybe we can come back on that, because this is a notion that can be important, because in general a capacitance is defined for a surface, but we can introduce a capacitance, a bulk capacitance, that give us this type of relation which exists actually inside the bulk. Yeah. It's just a question of interpretation.
Yeah, but yes, but actually in under the model hypothesis, if you have like some water with high concentration of positive and negative with equal mobility, usually everything is going to happen at the membrane. Like accumulation of this difference are going to happen at the membrane.
I meant that you can have enough heterogeneity in the bulk to create this effect. For example, in the case of it's even more clear in the case of non-electron neutrality, where you can have this. But in more general, you can think about a bulk capacitance because of the heterogeneity of the head.
Yeah, and also, so there is a question of, so there are many unknowns. You can imagine that you have no electron neutrality in the sense that you might imagine that you have no mobile negative charge. And also you can imagine that, because here we imagine a head that is a big ball of water, but you can imagine that you have a lot of organelles, and especially the ER, or I mean the spine apparatus, that could also contribute a lot to this capacitance and create some non-local phenomena. But this is like the simpler model, and then we can build on. And the second ingredient, so we have a potential that varies depending on the number of charge in the head, and so what happens in the neck. So here, I mean, I just dropped the analysis, but the idea is that you can simplify, reduce the analysis to a 1D problem. And I didn't put the reference, but there is an interesting paper of Kolinska and so Kolinska, this is the first author in PhysRev E. So they show how you can make the homogenization for a cylinder to 1D. And but the important thing that I wanted to recall is actually, and this is true for every 1D Nernst-Planck equation, is that you have two terms. So there are two forces that push the ion. There is a diffusion. Okay, so yeah, so there's a diffusion. So the diffusion is a gradient of concentration. So it's going to push both positive and negative ions from high concentration to low concentration. So it's going to push everybody. So typically, because the concentration is going to increase in the head, it's going to push everybody from the head to the dendrite. Okay, but and I mean, it took me some time to understand that when you have an electrical potential that increases in the head, actually it's going to push the positive charge from the head to the dendrite from high potential to low potential, but it's going to attract negative charge. So actually, if you have mobile negative charge, what happens is that you are going to take some negative charge in the dendritic reservoir and put them in the head. And actually this force, because the gradient of concentration initially when you have this voltage that increase is not that large, because I've just seen even with few charge you can have a big change of potential. But when you have a change of potential, this potential is going to push all the positive charge of the head. So these 10 million charge are going to feel this difference of potential and are going to be pushed towards the dendrites. And this is the same for the negative charge. So initially this because this is a current, this current is going to be very large, and this diffusion is going to be negligible. And I'm going to introduce the notion that actually in this type of process there is two time scales. There is a time scale of diffusion, which is more or less tends to 100 or milliseconds, and the time scale of electrostatic, which is in microseconds. And again, another hypothesis of the model. So all of these hypotheses, we'll discuss them in the conclusion, but another hypothesis of the model is that the dendrite is a big reservoir. But when you have some dendritic spines that are at the very end of some branch in a dendritic tree, and that the dendrite is more or less of the size of a spine neck, who knows what happens? I mean, you can then sense the influence of other spines all around. And so this is what I put here. So the flux of plus, so you can't see the flux of negative. So the flux of plus charge, so in this direction is the diffusion plus the current divided by 2, because the current is equal to this and this. And this is 2 because we assumed that this charge have the same motility. If you change the diffusion coefficient of negative compared to positive charge, then typically positive charge will be mostly responsible for the current and not the negative charge. And so based on this 1D analysis, so you can derive an expression for the diffusion flux and the current. So again, this is a first order diffusion. So the first order diffusion, you recognize something that is used to fit Frobbe experiment in this in the spines. So you have a gradient of concentration, Cn minus C0. D, so this is a common diffusion coefficient, as this is a cross section of the neck. So I have also a formula when this cross section is varying, is not constant, but again, this is a okay. So this is the reference to this 1D simplification of equation and expansion of solution. So diffusion, cross section, and length. And actually, it's completely to the like the first term of escape time in most common geometry, because you can have some nonlinearities, but this is the volume of the head, length, SD. So at the first order, let's assume that this diffusion is going to be proportional to this difference of concentration. And what is really interesting is for the current. So we have this very complicated expression. And so actually, if you remember the notion of electricity you did in high school, everybody told you that voltage is equal to resistance time intensity. So this is true in cable theory also when the resistance is constant. But here it's not, because the resistance is varying with the concentration, and the concentration is varying with intensity. Meaning that you have a neck resistance that is going to depend on the head concentration, and the concentration, as we'll see, is depending on the current. And so you have this type of logarithmic dependency, which make everything intercoupled and interesting. And so just to be clear, if C head tends to C0, then I mean, you're making an expansion of the log and of this, and then you obtain that the current is length kT to ESD, and here you just have C0, and so you have an expression for the neck resistance as constant concentration. And so as I told, the neck resistance can vary on the neck geometry, so typically the cross section and the length. And actually, you have a full spectrum of neck resistance depending on the length and the radius, meaning that, I mean, neck resistance can be high or low. So there is no, like, at least with this model, there is no discrepancies with all the experiments that have been done. But typically, if we put the boundary of high resistance at 200 megaohms, you can see that you can have high resistance. So for a concentration of 150 millimolar, and a diffusion constant of 1/4 of the diffusion coefficient in water, which is, again, an unknown of the model. You can have high concentration. Typically, if you take a length of 1 micron, which is really something common, for a neck radius that is below 50 nanometer, you will have very high very high resistance. And also, as we just saw, the neck resistance, even when you have like a constant length and radius, it can vary with the diffusion. So typically, if the diffusion is really low, for example, the effective diffusion in some really crowded environment, and is a concentration, so 1 is a minimum. You can also have like constant of more than 500 megaohms, and that's it. And then it decreases with the concentration. Okay.
Can you explain how you obtained those curves? So, for example, you injected different current.
Mm-hmm. Oh no, this is just a plot of this relation.
Ah, you just plotted this.
Yes. So I can make very C head, I can make very S. So what I did is that either I fixed the geometrical component, which is the cross section and the length, and then I make vary the other component, which is the concentration or the diffusion constant. Or I fix the diffusion and the concentration and make vary.
Okay, you just plotted. Okay.
Yes, it was just to emphasize that actually both the geometry and the physiological parameters can influence the neck resistance.
I understand. So, for example, the concentration in the head here, although this is something that can vary in principle, you fix it.
Yes.
You fix it.
Yes.
Okay.
Yes. So the first part is the static part. And then we are going to begin the dynamic part, which is the electrical potential and ion concentration is a slow and fast system of coupled equations. So again, when you simplify it, so you consider that you have some entry with some receptors. So because we are going to analyze some spontaneous activity with no NMDA response or very low response of NMDA receptors, we are going just to focus on AMPA receptors in our some geometry with this diffusion and electrical current in a ball and in a dendrite. So if you look at the mass action law of positive and negative charge in your head, so you have a head, a dendritic reservoir, you look at each time what is the number of positive ions that escape the head, what number of negative ions that enter the head, and mass action law. You obtain two equations, one fast equation and one slow equation. The fast equation is, in physics, that they call the charging of the capacitor, meaning that when you have some positive ions that enter through these AMPA receptors, are going to charge the head very fast, in microseconds. And actually the time constant, so the time constant is like the RC time constant in electrical engineering, and it depends because you have a very small capacitance here. Because the spine head is small, the charging is of the orders, again, of microseconds. So this is my current. So I have some conductance that can vary with time, opening and closure of channels. And it depends on this driving force. So here again, there is almost some computation. So this is H-King, Katz, and there is a third guy, Coleman, that derives this equation. And actually, this is just the I mean, the analysis is really interesting. This is the analysis of 1D PNP equation in a cylinder, in a 1D system. So you have this reversal. Actually, the reversal, based on some hypothesis, you can see that this is a log of C head over C0. And so it depends on C head, this reversal. And this is the I next, so you have phi head minus phi 0 because we made the hypothesis that the potential in dendrite is at phi 0, but again, it can change depending on the geometry of the dendritic tree. And this is the R neck, which also depends on C head. So here, everything depends on phi head and C head. So my two variables are phi head and C head. Phi head is my fast variable, that can vary very fast when you change the number of positive ions. And my slow variable now is this concentration. And the time constant here, this is based on the diffusion extrusion of ions, is more of the order of hundreds of milliseconds. And so okay. So just to show that actually this, for the fast system, this is so for 3 neck radius, 30, 50, and 100 nanometers, spine head diameters, concentration, and this is the charging time constant. So you see that the charging time constant is at most 1/10 of milliseconds when you have a very high neck resistance and very large spine head diameter and very low concentration. So in the most favorable scenario, this time constant of charging and discharging the head capacitor, like or the potential varies when you introduce some new ions, will be less than 1/10 of milliseconds. And okay, so this is, I mean, for me, this is the most important graph of the presentation. It tries to summarize what with this model happens in analytic spines when some ions enter. So when some ions enter, first they're going to charge, like these ions are going to accumulate at the membrane. So again, if you consider that this ball is something with water and equal concentration of negative positive. So it's going to charge. So you can see that, so this is 1/10 of microseconds, but let's say that after 1 microseconds, you have an establishment of a potential. And this potential, when it increases, it's going to drive a current. So it establishes a current. So it pushes some positive ions towards the dendrite and attracts some negative ions. And so you have this synaptic current that is going to decrease because it's proportional to potential of the head minus reversal potential. So if you increase the potential of the head, this synaptic current is going to decrease, and the neck current is going to increase quite fast. So after
what are the channel properties that you use for this current? It depends on the concentration between exterior and interior and stuff.
So we will see.
What are the equations for the channel properties that you use here and all this kind of things? So you depend on the conductance and all.
So this is an AMPA receptor. So you can derive.
You activate it with for some time and then you deactivate it.
So this is like this is just a scheme here. So you can imagine that you have some ions that enter and a sustained current. But after we will calibrate the opening and closure of channel and electrophysiological measures. Okay. But right now, imagine that you just inject an influx constant of ions in the head and see what happens. This is just to see the different time scale of the process.
So if you inject, they are already inside the spine?
So initially,
here, for example, it's true that usually there are two possibilities. Either the ions you start outside, and then indeed there is the models of probably having to use this capacitance, or you assume that already the charges are outside your channels, and then where you place them, for example, if there's this in the boundary layer of the channel, there might be some difficulty, or you can assume you neglect this and they're already in the bulk.
You mean on really like the injection site?
Yes, the injections, because if you inject, suppose you inject at the middle of the spine head, you can think that it can be different than injecting just at the surface, because here I understand you neglect it, but there is a boundary layer that can play a role. We looked at this a couple of years ago with Zev. So here, if you assume that it's as if you put everything at the center. For example, why you would have this capacitance effect that you have in your equation, right? Mm-hmm. There's no that capacitance coming from the membrane, because you just inject them really at the center. So this is like a bulk, again, this kind of bulk capacitance that you had.
Yes, but actually, when you have the excess of positive charge is going to redistribute very fast at the membrane, like in nanoseconds. It's going to move to the membrane very fast, the excess. This is the inverse of the first eigenvalues and of redistribution process. So very fast you're going to reach a Boltzmann distribution of ions through the membrane. But so here, yes, for sure we don't have these boundary layers that you can see and measure with some simulations here. It's impossible to account with. But the redistribution of charge at the membrane in this geometry is and so now we enter into the electrodiffusion, because you have a synaptic and a current that that very fast are going to equilibrate. And what happens is that the concentration is going to increase. Why? Why? Because here, so the current are the same. But here the current is only made of some positive charge. Here the current is positive in a sense and negative in another sense. Meaning that you need less positive charge that exit compared to the positive charge that enter. Because this is equal to this, but here you have plus and minus, here you have only plus. So typically, to simplify, if you have an equal mobility of positive and negative charge, half of these positive ions are going to stay in the head. And they are going to be compensated, because again, you need that the potential now has reached a plateau. So you need to compensate this arriving positive charge. And it's going to be compensated with some negative charge that enters the head. And so you can have a process that continues so on until a real steady state after almost 1 second. So, I mean, it's completely unphysiological. You cannot like sustain an activity and entry of ions for 1 second. But if you wait really a long time, at some point, you have very few positive ions that enter the head. And they are going to be because as the concentration increases, you have also a diffusion gradient of concentration that push positive and negative. So at some point, if you wait sufficiently long, you will not have any more negative ions that enter, and all the positive ions that enter here are going to be pushed by diffusion towards the dendrite. And so this is the graphs, because how much? So for different geometries, we have small head, large head, so 300 and 600 nanometer diameters, small neck, so diameter of 80 nanometers, large neck 140 nanometer diameters. And this is a change of concentration at this different time scale. So you see that initially in the electrostatics, you don't have change of concentration because it's too fast. But if you wait sufficiently time, you will have change. So the time is slower when you have a big head because you have a big volume. And the value of the plateau will be even more important, that the neck is tiny. And this, because we have seen that the neck resistance is decreasing with the concentration. So if you increase the concentration, you decrease the neck resistance. And the neck resistance for this tiny neck, initially with the parameter of the model, is around 40 megaohms, and it's going to drop to less than 300. So almost one third drop. And this is the same for the red curves, but initially the neck resistance is much lower. And this is what happens to this reversal potential, because as the concentration increases, you are going to decrease this reversal potential by almost up to 10 millivolt. And this is a synaptic current. So this curve is interesting. So initially you have a drop due to charging the capacitor, and so decreasing a lot the synaptic current. So at some point it equilibrates here. This plateau is when the synaptic current is equal to the neck current. And if you wait sufficiently long, there is a small other drop, which is due to the decrease of this reversal potential. And finally, what happens to the head potential? So when you put some charge, very fast it's going to reach a plateau in tens of microseconds. So initially we took minus 58 millivolt, and up to, you see, you have a depolarization of almost 30 millivolt. Then you have this plateau, and then you have a big drop. And this drop is a combination of a decreased neck resistance due to increased concentration and a decrease of synaptic current due to decrease of reversal potential. So you have both effects that are going to combine and decrease over a long time the head potential. And this is a curve that you might have seen on Monday. So this is like the linear voltage equal resistance time intensity, and this is what is predicted by PNP at steady state. Because at steady state you increase the concentration, and the concentration is dependent on the current, and this is a formula. Phi head at infinity at steady state is something, so gamma, this is the inverse of 25 millivolts, is a constant, and you have a log of intensity. And David and Jerome obtained the same formula recently, also in, I don't know if the paper is accepted, or at least it's on bioarchive. Okay. This is a saturation. Okay, let's just keep this, because I would like to now, in few minutes, emphasize what we obtained with some electrical recording. So this is what my colleague Krishna did last year. So this is a dye. So he had a nanopipette. So this is a specialist of electrophysiology, of nanophysiology. So he has a pipette. To see where his pipette is, he has some dyes. And this is the tip of the pipette, and this is the spine. So, I mean, I would not be able to do this, but he was able to do this on four spines, I think. He inserted the pipette in the dendritic spines, and then he used a lot of deconvolution of electrical engineering to measure the voltage directly inside the spine. So here it's here it enters, and then he can measure the spontaneous voltage, which actually were quite high. So it seems, but there is a bias, because he put the pipette into like long spines, okay? Because this is a spine that you can see. And so this is the first report of direct voltage measurement in the spine. But what interests us is that we can have the dynamics of one PSP. So you see there is not this shoulder that would be a mark of an NMDA opening. So let's assume that this is only AMPA receptor opening. So you have a very fast increase and a quite slow decrease, but overall the process is like 10 to 20 milliseconds. So it's slower, much slower than electrostatics, but much faster than diffusion. So what happened? So our conclusion is that actually the kinetics you observe with this spontaneous activity, this is the kinetics of channels. This is the opening in less than a millisecond and the closure in less than 10 milliseconds. And so what we did is that we took this measurement, we did an estimation, a modeling of what would be the synaptic conductance. So we took a model with a sigmoidal opening and a mono-exponential closure. So we have three constants in the model, mu and τ1 for this sigmoidal opening, and τ2 for the closure. So we made like some 4 measurements on these 4 different PSPs. Interestingly, this constant, so for each geometry we used, so large head, large neck, small neck, this constant didn't change except the amplitude, because the amplitude is going to scale with neck resistance. And we can then estimate the synaptic conductance as a function of time, plug this into our model, estimate the voltage, and compare the trace with the initial trace with some least square, just a least square fitting. And we obtain, so based on this, we can plug into our electrodiffusion model some conductance. And what is, I mean, I was the first to be surprised that actually even with this conductance, at this time scale, so you can see that the channel is open for like 10 milliseconds. So even during 10 milliseconds of opening and this amplitude of current, you can actually observe, so depending on the geometry, dramatic change of concentration, up to 50% in the most favorable case, which is small head and large neck, because a large neck then you need a big current to sustain the observed voltage. And actually you see that the trace is here the decay of the concentration is much slower in large heads. So this is a dotted line. And so this is associated to a large variation of neck resistance up to 15%. So for one single spontaneous PSP. What could happen now? Because this is something, but you see that for each PSP you have a change in concentration, and as we have seen before, the change of concentration is quite slow to come back to the steady state. So you can imagine that if you have a sustained activity, then you could build up on this concentration. So we made some simulations because you can imagine that experimentally it will be very hard. So we took just two different neck resistance, 100 and 500 megaohms, at two different PSPs, 20 or 50 megahertz, 50 hertz, excuse me. And then we can see that you can build on concentration, especially with neck with high resistance, and so decrease the resistance. So meaning that, I mean, one hypothesis of all of this is that when you have a sustained activity on the spine, even without any long-term potentiation, you could quite fast, in less than 300 milliseconds, you could already have some like short-term potentiation just due to the accumulation of ions inside the spine head. So this is a conclusion. So this is an electrodiffusion framework. So electrostatics is much faster than diffusion, and both are equal. The PSP rising and decay phase, this is opening and closure of channels. Concentration can change even during spontaneous PSP, and this concentration might build up during sustained activity. And now just to finish, I would like to emphasize future questions like add-on on this model, like the reduced motility of negative charge. What would happen if you have only positive charge? What happens if you have a complex shape, and especially a spine apparatus, the ER? And so for these first two, the fact that you have only positive charge, this is what David discussed, then it leads to something that is completely unexpected, because if you only put some positive charge in some water like this, I mean, it's like almost a plasma physics. You have like long-term interactions between all the positive charge, and they all repulse each other and accumulate as a membrane. And so all this classical theory of the bilengths, etc., completely, I mean, it cannot be applied. And another extension is the ER, because, I mean, the effect of the ER in the spine apparatus. So I thank Heidi for showing me this picture, so I took the same. So in this picture, you can see that you have, I mean, if you put this spine apparatus here, you are going to reduce the volume, so the change of concentration are going to be much faster. But at the same time, you are also going to increase the effective membrane capacitance of the spine. Also, this geometry of the neck junction, which is really important to regulate the flux and especially the diffusion flux of ions, is going to be completely changed. The neck resistance is going to be decreased because the effective cross-section of the neck is going to be decreased. So, who knows what would happen with this? And okay, so thank you. So this is a PI of my lab, Rafael Yuste. This is Krishna. So Krishna did all of these electrophysiological measures, and we discussed a lot about this model because it's coming from electrical engineering. So we try to build something that makes sense from an engineering point of view and which is mathematically correct. And now Krishna got a position at Purdue University, so he started his lab in December, and he asked me to make some announcement because he's looking for students and postdoc to work on electrodiffusion. He has plenty of ideas. He also wants to put some hundreds of electrodes in the brain and record and do some analysis. So he has a really interesting project, and he's a really good mentor. So this is all so this is Columbia University. So this is our support. So for Krishna, is is Kafli Fellow. I have been supported by FRM and Philippe Foundation. And this is the financial support of the lab. And so thank you. And so this is a view of the lab. No.
Questions? I think Eddie is ready for a few questions.
Oh, yeah. I have two simple questions. I mean, first question is maybe you know regarding this amazing recordings from spines. You call it spontaneous EPSP. How actually you sure it's EPSP and not, for example, propagating spike or whatever? I mean.
So first I would say I don't know. I mean, I'm not sure. I said it was spontaneous activity, but it might be not. But on the other hand, so I could have Krishna, but I don't know if he was able to also put some classical electrode in the afferent neurons. But this seems quite difficult, so I'm not sure he did it.
But, no question about it. I just let me reformulate maybe. Did he have also another electrode in soma of the same cell to compare these two signals from spine and cell body? Then, of course, you can.
Yes.
I mean,
so
understand.
This he had. Yeah.
This he had. So perhaps
yes.
he could see that it's local.
But to know if this is a spontaneous, like a PSP, or if this is an afferent. Backpropagating. No, it's not. For sure, it's not. No.
This was my question. Yes.
Well, I wonder if you were telling about what is the activity of the afferent.
Oh no! It's too complicated. You know.
No, but yes,
I don't want miracles. I mean.
No, because he can estimate the neck resistance.
Okay.
So what he doesn't have is an electrode at the base inside the dendrite. So he has to estimate what would be the dendrite.
Perfect. That's all. That I didn't see the paper itself, so that's why I asked. Okay, but yeah. I will check it too. And my second question is very stupid. I mean, I'm really sorry. Perhaps I have these long spines, as you have mentioned. When we imagine this classical biological membrane in rest, we believe that along the membrane there are negative charges, right? I mean, and the positives are on the outside of the membrane, while negatives are along the membrane inside. Is it? I mean, at least that's how it is described in textbooks. I mean, I don't know if it's a correct picture to imagine, yeah? And then we take some positive ion, like calcium or sodium, which will pass nearby. My question is very naive. Does it feel this accumulation of negative layer and it can't come close to the membrane? Should be somewhat a part of it because there are like forces, or vice versa. It will like be pulled to this negative layer and get stuck there because it, you know, plus likes minus. I mean, in this boundary layer. That's what I mean. I mean, it can be important. It's not important at all if you have big space, but if you have narrow space, such as spine, neck, and especially if you consider some additional structures inside, then the lumen may be very small, and then this effect can be important somewhat. Yeah, I mean, do you know?
Yeah. So actually, I mean, in this type of electrolyte with negative positive charge, what happens is that you have some negative charge, and then you make like a sandwich. Like you have positive charge that comes, and at some point you enters the bulk where everything is like water, electroneutral. And here, in the dimension we considered, we just didn't consider this boundary layer. But for sure, if, for example, the neck junction is very small due to the ER, and then you have maybe 5 nanometers to pass through, then again all this theory breaks. You have to redo everything. And I'm not sure that you can do anything analytical. I think that at some point you need some Monte Carlo molecular simulations to see what happens, because it's going to be too complicated, because then you have also the steric effect, because at this dimension, ions, the size of ions is going to be significant.
Definitely. I wouldn't be so pessimistic about your ability to calculate it. I mean, I do believe with new computers and huge power, I think it can be possible.
Krishna is doing a lot of simulations to see exactly what, for example, happens at the tip of the nanopipette, because he has a tip of 10 nanometers with big difference of concentration, like 300 millimolar in the pipette and much less below. And so the interface, he observes a lot of interesting phenomena.
Okay, thanks.
So maybe this is a general question that maybe we can discuss here. If you look at the concentration of sodium, the free concentration of calcium, which is very small, and the concentration of potassium, to counterbalance these positive charges, the chloride is not enough. And so this is clear that if there is electron neutrality, it doesn't come from chloride, obviously. And so this is something that is not very well debated, that where the extra negative charges is coming from, where they localize. For example, they can come from the membrane, but we've seen that if indeed there is this very high accumulation of negative charges, probably you have these Debye lengths because of the water. Nevertheless, you can have all of these negative charges coming from this floating protein that introduce a new time scale because they diffuse. I mean, yeah. So maybe you want to comment on this, because assuming non-electron neutrality by another estimation of positive charge probably is one extreme. Going into electron neutrality at any spatial scales is also another extreme. So probably there is a scale in between. I don't know if somebody wants to comment on this. I think this is probably something to think about for the next generation of model and simulations. So, any other questions or comments? Okay, so let's stop here. Let's thank Thibault again. And now we have a coffee break for, let's take 20 minutes.
Am I on? Yes.
All right, let's resume this morning session with Kyle Wedgwood. I hope it's okay.
That's close enough.
From Exeter University. It's a pleasure to have you here. Please, Kyle.
Yeah, thank you very much. And thanks everyone for sticking around on what looks to be a lovely sunny day here in Pisa. So I will make a disclaimer right now. So I'm kind of a relatively last minute stand-in, so I'm not actually going to be talking about a lot of the stuff that certainly I've heard about. And for those of you that are wondering, I haven't been here all week because I was actually on holiday. But it seems from what I've heard over the day and a half that I have been here, it's been a fantastic meeting. And I'd just like to thank David and Krasi for having me here. So this is Exeter. For anyone who's not been, I would recommend that you come. It's a beautiful little city in the southwest of England. And when I got invited to give a talk, I was trying to think about what I could talk to this community about, because a lot of the stuff that I've done in the past has been relatively abstract. So my background is applied mathematics. I heard yesterday people sort of apologizing for their background. I suppose that's my apology. So some of this will be modeling, some of this will be theory. I hope that in spite of the fact that it's not really addressing any of the sort of key themes that are listed on the meeting, that you will at least find some of this interesting. So what I'm going to talk about are these grid cells, and I'm going to talk mostly about sort of the general physiology of grid cells, but also we'll discuss quite relatively briefly aspects of dementia, and in particular a mouse model of dementia that we've been looking at. This will all be at the whole cell level or network level, so it's kind of, you know, at least one scale, probably two scales up from a lot of the talks we've been hearing about. So it's kind of, in that sense, more sort of traditional applied mathematics with a little bit of novelty at the end. Oh, come on. Here we go. So the general outline of the talk is this. So I'm going to give a very brief overview. Well, it's actually not that brief, but a brief history of grid cells and their discovery. So I imagine most people will be at least familiar with the name grid cells and probably even what they do, especially following the Nobel Prize that Edvard and May-Britt Moser shared with John O'Keefe for their discovery. That was back in 2014, I believe. I'm going to go through sort of the sort of pre-existing mathematical frameworks that have been used to explain their behavior. And there has been a number of different approaches that are used. I'm going to focus on two of them. There are others, another disclaimer. Then I'm going to focus a little bit on some of the physiological characteristics that our collaborators have highlighted that they think are important. And in particular, there's one very specific phenomenon that you see in the entorhinal cortex where these cells live that I really want to focus on. And then finally, getting into sort of the stuff, the projects that I've been involved in. So there's going to be some single cell modeling, which will be based on an ODE framework, and then network modeling to explain the grid cell patterns. So this story of grid cells really starts back with John O'Keefe's experiments in 1976. And what this is really highlighting here, so this is a little, well, they call it a maze. It's not really a maze, it's just an environment that a rat kind of wanders around in. So you imagine, you know, this is sort of a meter and a half kind of diameter circle, and then there's little arms out here. And then what you do is you implant electrodes into the rat's brain, and here is the hippocampus, and you just measure signals. Okay, so these are extracellular recordings, but in vivo. And the idea is that as the rat moves around, you see activity in these different parts here, right? So you can see when the rat is at position A, you start seeing activity in electrode in position 1. And then when the rat moves around or sort of does something, you can see activity here. So as the rat is moving from D to A, you see an upregulation in activity in this here. So this provided some evidence that there are cells in the hippocampus that are really telling you something about where you are in space. So it's as if you were looking top down at sort of the floor plan here, and there are cells then that have receptive fields that are literally in your physical location. And this was the first real evidence of this. And later on, this was then quantified in a follow-up study where these are basically plots of these receptive fields. Okay, so again, there's an environment which is now a square. You play the same game, you implant electrodes, and you measure activity as the rat is moving around the environment. And you can see that, you know, sort of very, very roughly, these things kind of look a bit Gaussian, or here, I guess you've got a bit of a bimodal thing. But if you look at the evoked activity as the rat is moving around, you can see a clear receptive field for these cells here. And these were called place cells. Okay, so John O'Keefe was the guy that did basically all of this work, and he shared the Nobel Prize with the Mosers. So these are place cells, and it was postulated actually long before even these kind of experiments that there should also be cells that encode so-called grid-like patterns, and these are quite funky little cells. So the way this kind of works is, again, right, so imagine that this is now a circular maze. Okay, so again, this is a big environment that the rat can run around in. And now what you see, as the rat is moving around, so each red dot is like a spike or sort of an evoked potential. And as the rat is moving around, you can see that there are certain points on a grid that these cells or these regions are active. And if you cross-correlate this activity, you find patterns that look like this. Okay, so these are 3 examples of so-called grid cells. And the idea is that they fire or the cells are active on the vertices of a hexagonal tiling of the environment here, right? So if you took this room now and you laid down a hexagonal lattice, as you would walk around, you would see activity along the vertices. Okay, and so these were called grid cells. They were discovered back in 2004, 2005. And there's been a lot of real interest in this from both the mathematical community, because it's a really interesting problem in pattern formation, and also in the biological and neurophysiology community for reasons that I'll explain now. So these cells live in an area called the entorhinal cortex, which provides input to the hippocampus, which I'll discuss in a little bit. But these are not the only cells that make up the story, right? So there's been a whole bunch of other cells, which, oops, hang on. Sorry, this thing is a bit stiff. Okay, so there are lots of other cells that complete this picture about how sort of we encode sense of place in our brains. I'm just going to mention 3 of them. I'm sure as the field progresses, there'll be more and more cells that are discovered. So there are these so-called head direction cells. So here you have a little rat with a camera above him. And again, you implant an electrode, and now you're interested in what orientation is the head. Okay, and you can see receptive fields here that are now aligned to preferred directions. Okay, so there'll be one of these for pretty much all of the angles you can get around, because rats are pretty good and can get their head around almost 180 degrees. There are also the so-called boundary vector cells. So obviously as I walk around this room, there's sort of chairs in the way and I guess bags and whatever. So these provide obstacles, right, which I have to be aware of. And so they did an experiment here. So the rat is now on a raised platform. Okay, so there's like an edge of the thing. And again, now you find cells here that are active along the boundaries of this. And you can see here that these are just 4 examples. In this paper, there's a nice paper here by Neil Burgess' group where they document hundreds of these things. And you can really see patterns of boundaries emerging. And then more recently, it had been proposed that there's a so-called speed cell that tells you about how fast you're moving. And in 2015, this Nature paper basically did this experiment. So you have a rat running along a little treadmill, and now you can see that there are cells whose firing rate is proportional to the actual speed that the rat is running at. And so the general idea is that, you know, somehow these, yeah.
How do these measures in terms they look at the leg movement, or they look at some visual information, or?
For the speed cells?
Yeah.
So the rat is basically powering this little treadmill here. So they know how fast the rat is moving along. So the rat is fixed in space, but can run along this treadmill.
So there are some muscle input to get some input from the motor neurons or something.
Well, so they don't measure specifically the motor neuron input here. It's really just a direct readout from how fast the rat is moving. So the rat is fixed in place, but can run.
I understand, but these cells, they must somehow measure the speed.
Oh, you mean these cells? Oh, right. So I don't know exactly. These cells are not the same cells that are providing input to the motor neurons. These are
probably the motor neurons provide input to these cells.
Right. Yeah. Exactly.
They
exactly.
Get out a speed, something. Like
yes. Almost certainly that's the way it will be.
Yeah. And so what was the difference between grid cells and place cells? The grid cells are outside and the place cells are in the hippocampus, but it's more or less the same kind of thing, or?
So that's a good question. If I may, I'll come back to that. Okay, so the idea is that then you think, well, these are pieces of a puzzle, and the puzzle is, well, how do you get from point A to point B, or how do you plan to get from point A to point B, right? So if I know that my car is parked, somewhere over in the main square, I need to navigate from here to there using information that I've collected. And so this sort of partially addresses this question, but I'll come back to it again in a second. So if you look at where these different cells are, and I'm just going to focus on the place and the grid cells primarily. This is a bit small, but essentially the place cells are in the hippocampus and the grid cells are in the entorhinal cortex. And as for what the differences are between them, this is an interesting question in the sense that it has been postulated at least a couple of times that a place cell is basically just a grid cell that effectively has just one receptive field. So if you imagine the grid is sort of too big to be realized by this particular anatomy. However, I think that kind of hypothesis has sort of gone away a little bit. The head direction cells sort of appear anyway. But sort of this is sort of addressing this. So this is an example of a staining with a rabies virus where they tracked the projections on the place cells back essentially to the entorhinal cortex and to the grid cells. So then it's very, very tempting to think of a model of place cell formation that goes like this. So here's a bunch of grid cells. You want to know how to make a place cell, and you've got all of these grid cells that are sitting around in the background. So why not take the output from some of these grid cells, which we know project into the right region in the hippocampus, and basically take a weighted sum of different subsets of grid cells, and you can make a place cell. Because effectively, or you only get firing at overlaps between these different grid cells that may have different spatial frequencies. So some of them have sort of a very high spatial frequency, and some have quite a low spatial frequency, and I'll come back to this later. So this is sort of a popular model for how you make place cells out of subsets of grid cells. Although I will say that there was a study done in 2014 that basically says developmentally you see place cells before you see grid cells. Okay, so this implies that even before grid cells have even started, acquiring their cell fate, that you see place cells. So at most, in the sort of the adolescent rat, they're playing a regulatory role rather than actually providing the input to stimulate these place cells. However, there have been all sorts of follow-on experiments where they've looked at different scenarios. So one of my favorite hypotheses is about how you integrate information contextually, right? So in an environment like this, I'm quite happy to use my place cells because I can see everything, right? I can see all of the obstacles I need to get out. I can see the door if I need to get there. However, if I switch the lights off, I don't have any way of sort of knowing where these things are. And my memory will store my information of place over short times, but as I move around, this drifts. So you require visual input to reset these place cell maps, whereas the grid cells are much more robust, right? Because you've got this nice tiling property. So they did some experiments in rats where they effectively did this, right? So they put them in the dark, and they saw an upregulation in grid cell firing compared to place cell firing. So the point is, though, that this may well be true, that grid cells provide input that sustains place cell firing, and that's how we navigate. But the point is that even outside of this this potential pathway, there's a real interest in understanding grid cell patterns. Oops, come out. Okay, so how have people thought about describing this mathematically? Well, I guess one of the first models that really came about is this so-called oscillatory interference model. And what this model does is it says, well, we know that there are head direction cells that have preferential firing or receptive fields that are oriented at certain angles of where you put your head. And what you can do is you can say, well, these then provide input to the grid cells in such a way that, so there is activity in the dendrite, which is now just given as some sort of oscillation. You can talk more about the sort of the neurophysiological foundations of what this oscillation is, but in the context of this model, it's just some oscillation, and that is phase shifted by the preferred direction of that cell. Then you assume that the soma of that same grid cell has at some frequency of its own, and the idea is that you sum these guys up and you take input from a variety of different head direction cells, and then the firing rate that you get out will look a bit grid-like. And by that I mean that if you imagine that there's a path that the rat is moving around, you will see firing on the edges of this hexagonal hexagonal lattice. I'm not a big fan of this kind of model because it does work, which I will show here. So here's an example of what happens when you just have, okay, so this is just a linear run, so just a straight line, and you take one of these inputs from these head direction cells. Okay, that sort of doesn't look that nice, but as you increase the number of distinct inputs you get, you get grid cell-like patterns. Okay, so these are basically the average trials, and then these have been smoothed by a Gaussian filter, and you can see, you can pick up these same receptive fields that you would expect in experiments. The downside to this is that this really only works well if your head directions or the input that you receive are from cells that are really set up in the correct sort of orientation. And by that I mean, so for example, for 3 distinct inputs, you have a 60-degree offset with your preferred head directions. Now that might be true, and there's sort of a lot of evidence to suggest there are cells or projections that sort of go like that, but it requires an awful lot of tuning even before you've established the grid cell. So I mentioned this primarily for posterity. I'm more interested in these kind of models, these so-called continuous attractor models, which look like, well, look basically like this. So what you do is you build a network already that is pattern forming, and there are many, many examples of this, and have been for a while now, since sort of neural field theory and the kind of things that I've done. So this was sort of dating back to the 70s, so these models already kind of exist. And then what you do is you take the inputs from the head direction cells and the speed cells, and then you move these patterns around, and then the firing activity that you observe if you measure the activity at any particular point in the entorhinal cortex would then look like a grid cell. And it basically goes like this. So say you have some sort of coupling function with some sort of lateral inhibition, and I might just have to click this button because this is really... And then what you see if you take then a whole bit of tissue is you see patterned activity, and it's very, very easy to generate these hexagonal lattice patterns. In fact, you can demonstrate mathematically that actually this is the kind of solution that you would expect with a coupling kernel that looks like this. And then you can have parameters in this. So the parameter that defines the width of your lateral inhibition will then set a spatial frequency. Okay, so this is something to have in mind for the sort of second half of my modeling discussion, but I'll bring this back up again in a little bit. And sorry. And so this is kind of what the model looks like. So you have some activity variable SI, so the I is just encoding some location now, physical location of the neuron or population in the actual cortex. And then in the absence of any activity, it just decays with some timescale tau. And then what you do is you take weighted input, so this W here encodes this lateral inhibition, and then you just have some offsets that really are coming from the directional biases of these head direction cells. So the W here is encoding the lateral inhibition, which will set up these patterns, and effectively you can calculate steady states of this that then give you a hexagonal tiling. And then so imagine then that you've got an electrode that's here, and you're moving along again in this sort of a lateral path in this direction. So you'll see activity, then nothing, 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 and then activity again. And as I said before, you can scale the lateral inhibition width of this coupling kernel W, and you can generate any kind of grid cell spatial frequency you want. Okay, and finally, in terms of the modeling, just to say that both of these kind of ideas for grid cell models essentially rely on sort of this path integration kind of idea, whereby that you have either a continuous attractor in the shape of some sort of bump or hexagonal pattern, or you have some oscillatory interference signal, and then effectively what you do is you integrate information from other kinds of cells as you move around, and what you do is you build up a representation of this trajectory in space, and then you can use this if you have inputs from lots of different layers of head direction cells, you can build up a representation of space. And so all of this stuff has been done in rats primarily, and mice to a lesser extent, but there has been a sort of interesting experiment which has taken advantage of new VR kind of environments where they do this kind of thing. So they give you a headset and you're in this virtual environment and you're asked to go find a thing, right? So it's like a little treasure chest or something. So you walk around in this virtual environment, you find the treasure chest, and then it puts you somewhere else and gives you these visual landmarks around like these mountains, and they remove the treasure chest and they say go back to where you found it. And again, they can measure fMRI activity, which is not quite the same as sticking an electrode in your head, and so you should take this with a little pinch of salt. But again, you can track out the trajectories that people have actually physically now walked in this virtual environment, and if you take the activity and you cross-correlate it, you get something that looks a bit like a grid cell. Okay, I mean, there's going to be lots more that's going to have to be done to really confirm that these really are the same kinds of cells that are in rats, but at least it's sort of first evidence that these exist. And it's a nice kind of experiment to integrate these sort of hybrid ideas. Okay, so that is kind of a sort of a brief history of the modeling and discovery of all of these different kind of cells. I want to tell you now about some of the stuff that I've been doing, and in particular with reference to one specific phenomenon, which is to do with gradients in grid cell spacing. So we talked a little bit about this, and it's a bit dissatisfying in some sense that you can get grid cell spacings that are different, but it relies on you setting up differences in your lateral inhibition. This seems like a little bit of a cheat because you're basically just getting out of the model what you put into it. And moreover, we know from our collaborators at Exeter that you see, well actually, so I'll come back to that in a second, but you see gradients in intrinsic cell properties too, along a very specific axis. So, okay, these dots are a little bit hard to see, but basically what we're doing is we're sort of moving through these slices and also sort of kind of along this direction here. And the point of this is to say, well, as you move along from a dorsal side to the ventral side along an axis in the entorhinal cortex, what you observe is you see that the grid cell spacing increases. Okay, so you start off sort of quite close to the dorsal end, and you get very high frequencies. As you go through, now we're sort of about 70%, you see big grid cells. It is not necessarily the case that this is a linear gradient. So there has been papers that have come out and have shown really modular kind of things, right? So you have small grid cells, sort of medium grid cells, bigger grid cells, really big grid cells. And actually this has been known even since, so this is data from a Brun paper from the Moser group, but actually this was reported right back when grid cells were first found. So we've known about this gradient in grid cell spacing right back from their initial discovery. And if you have a look at single cell properties, you can see some of this already, right? So this is part of the reason why we're interested in looking at intrinsic properties. And one of the things that I'm going to talk about in this first part is this thing here, right? So this is looking at the actual firing activity in these stellate cells in the entorhinal cortex. And they're interesting from the perspective that they fire in a very kind of irregular pattern. At the dorsal end, it looks more like little, well, they're called clustered spikes. I mean, the mathematician in me would call them a little burst, but they don't like that terminology. So they're clustered spikes, whereas in the ventral end, they look a lot more regular, more tonic. And so I said before that I was going to tell you a little bit about dementia. So this particular study that was done by collaborators in Exeter was looking at a model called the TG4510, which is a model of dementia that involves little tau protein bundles that essentially form inside the cells and mess up some of the intrinsic properties of the cells, but not the coupling. And what you see in these cells is that this gradient is essentially abolished, right? So the firing activity now at the dorsal end looks pretty much exactly the same as the ventral end. And you can see this here. So the blue is the transgenic, the black is the wild type, and then here it's essentially plotting some AHP amplitude, and here is the sort of more important thing for us. You can see that this gradient from dorsal to ventral is effectively abolished. Okay, and this is going there. So to measure this, I just want to say this is the experimental metric that they use to describe this clustered firing, which is the same that we do in our experiments. And basically it says, well, a packet of spikes is clustered if the interspike interval between you and your nearest neighbors is, say, less than 150 milliseconds, and there is a gap of at least 250 milliseconds before the next spike. Right, so here are 4 different spike packets. So the first one is clustered. So these are 3 clustered spikes. Here they're not clustered because the gap between them is too long. Here the first one is not clustered with the second 2, again, because the gap is too long, and so on and so forth. And then the idea is that you take a measure, P clust, which measures the burstiness of the cell, where you just take the number of clustered spikes and you divide by the number of total spikes in, say, a 10-second recording. Okay, so that is the experimental setting, and this is the question that we're trying to get a handle on in this single cell model. And what we did was we took a model that was sort of the classic Hodgkin-Huxley type. So I said that this was going to be a sort of more of a standard ODE framework. So it has a whole bunch of different currents that are involved in this. A lot of these are sort of the standard currents that have been discussed before in the entorhinal cortex. So you have some sodium currents, transient and persistent, these potassium currents here, and and basically these sort of first 5 currents here are we think of as basically just the spike generating mechanism of the cell. We're much more interested in these 2 currents here, so the IH current, so this is a hyperpolarization activated non-selective cation current, and an AHP current. Now I will say again as a slight disclaimer, we don't have a full handle yet on what is actually providing the AHP current in these cells. We think that it's to do with things like BK channels, but we don't know quite yet. So part of this work in the future will have to be to characterize really what this is about. But effectively, these guys, they follow the standard kind of Hodgkin-Huxley formalism. And this is, and we also include a delta correlated noise term here, right? So we want to study noisy spikes. Yeah.
So these currents are all known for this cell. It's not the standard Hodgkin. So this is specific for these cells.
Yes. Sorry. Yeah. Right. So the formalism of Hodgkin-Huxley, but it's been tailored to this cell type. Yeah, that's a good point. Okay. So here then is the result of just doing a simulation of this model, where we report here this P cluster metric that I discussed before, and we vary 2 conductances here, one to do with the AHP and one to do with the IH current. And effectively what this is trying to demonstrate is that, let's say you fix your AHP conductance and you just take a walk vertically upwards in this parameter space, and you can see here you start with kind of sort of noisy subthreshold activity, and as you go up you start going into different things like here, and as you move up you see this guy here looks like clustered firing, this guy here looks like tonic firing that we saw at the ventral end, and this is basically just quiescent. Yeah.
I'm having trouble understanding your color code. So right. The uppermost one, which looks like tonic firing, is solid yellow, which should have a clustering fraction of 1. Right.
Yeah. So okay. So this is a slight. What's the way to describe it? It's kind of a bit of a bogus thing in this region here, right? Because basically what this is doing, you either set this really to 0 or you set it to 1, and perhaps it would have been more useful to set it to 0, because what this is doing is it's counting all of these spikes and then basically saying, well, this guy had nobody before him, this guy had nobody after him. So it's saying that they're all part of one big cluster that is the entire duration of the experiment. But yes, actually it would make more sense if this were 0, because that's what it's supposed to be. Yeah, that is something that I should change in this graph. But effectively, I mean, the main point that I'm trying to make here is that sort of there's this nice region here where you can sort of pick where you want to be in terms of P-cluster. And we actually went through this and we said, well, okay, so we've got freedom to pick where we want to be in terms of the model, and you can get some very nice fits to data with sort of reasonably small values of noise. And then the applied mathematician in me says, well, okay, so this is a stochastic model because we've put in a noise term. Can we explain this by looking at the bifurcation structure of a deterministic model where we effectively set sigma to 0? And the short answer is, well, kind of yes, and I'll explain this a little bit more later. So here the color code now is the number of spikes per cluster, or burst, I guess, if you like. And so this is just a simulation plot where you effectively wait for transients to disappear, and you literally just count the number of spikes. Okay, and here you can map on these points to these points here. So you can see sort of a 2 packet here, 3 packets here, and of course, you know, when you put noise in, these things get jittered around a bit. So sometimes you miss spikes, sometimes you get extra spikes. But okay, so now the question is, well, what is mediating these transitions? And so what we did was we did a 2-parameter continuation using Poincaré sections, and effectively, unsurprisingly, you can find these boundaries by looking at the linearization around a well-chosen section. And you find different kinds of bifurcations. So you see a lot of flip bifurcations, and sort of where you essentially add in extra spikes to your cluster. And you also see saddle node bifurcations that take you from rest into spiking, and flip bifurcations that take you from tonic spiking into some sort of clustered firing. And you may look at this and think, well, it's not immediately obvious that that's what's going on. You can sort of see it when you pick a point in the stochastic simulation in terms of parameter space and you compare it to the deterministic. However, and actually it was a reviewer that suggested to do this, when you plot the mean firing rate or mean number of spikes per cluster, you can see much better sort of relationship between the deterministic case and the stochastic case. Okay, so the idea is that we can set more or less where we want to be in terms of p-clust, at least in terms of an interval, by looking at the deterministic bifurcation diagram. So coming back to dementia then, how does this help us to decide what we want to do? Okay, so what we're showing here is the difference between the p-clust value that's reported in dementia for the dorsal end in two conditions, so in the wild type and in the TG4510. Okay, and the color code here is that the red is where the fit is really good and the blue is where the fit is really bad. Okay, and the point is here that you can then look at this and you can say, well, given these two parameters, what is a sensible thing to assume has happened, right, to this cell? And moreover, we can say that there wasn't an awful lot in the experiments reported about the conductance of the IH current. So therefore, we concluded that basically these two different routes here, so either coming from a tonic firing into a more clustered firing, or essentially moving through so these different clustered states, this is a potential mechanism for generating the same kind of data as we see in the transgenic mouse model. There were some regions, this is not super important, but there were some regions where analysis breaks down, and we were kind of wondering, well, why can't we do this? And it turns out that this is a very expected phenomenon that you see in these kinds of sort of bursting systems, where as you progress from sort of a tonic pattern to a clustered firing pattern, you go through this region of chaos. And effectively, this is what this is showing by this Poincaré section here. Okay, so now we've said, well, we have a proposed mechanism for taking us from the wild type to the dementia model, but it relies on knowledge of where these clustered firing activity comes from. And we've looked at the firing patterns of the deterministic system, but the question is, well, where do these burstings come from? And of course, here we can rely on the same kinds of ideas that Thibault talked about before, which is essentially a singular perturbation expansion in a small parameter, where our small parameter now is one of the timescales. So we separate our model into fast bits and slow bits. You can look at a fast system where you treat the slow variables effectively as parameters, or you can treat the slow subsystem as effectively being restricted onto a space where your things like voltage and your currents have to evolve along a certain manifold. And when we did this, we said, okay, well, what is a natural selection of our fast system and our slow system? So it turns out that there are two parameters, or two variables here that correspond to a slow system, namely the activation of the persistent sodium and the inactivation of one of our potassium currents. And moreover, quite happily, they sit effectively along a straight line. So we said, well, okay, well, let's just pretend that this really is a straight line and simplify our model so that it looks like this. So we have one slow variable that is equal to the activating gate for the persistent sodium, and then we just treat this other gate effectively as just an affine transformation of that one. And when we do, and when we do this, okay, we can plot a bifurcation diagram now in our fast system, and actually all of the interesting dynamics happen in a very thin line around here, which is blown up over here on the right, which basically says that you get bursting because your slow variable pushes your fast system through a subcritical Hopf bifurcation, so you start to get these big oscillations, and then these are terminated in a homoclinic connection here. So the idea is that, effectively, sort of the bigger this distance here is, the more spikes you get, because it takes you longer to get back down to this homoclinic bifurcation. So the idea is now that what we've done is we've gone through, we started with the stochastic model, we have understood transitions between bursting by looking at bifurcations in 2-parameter space of the deterministic system to understand where our P plus values come from, and then we've taken that back to a fast-slow decomposition to understand the origin of bursting, and so now we have a good understanding, at least from a mathematical sense, of how to set up our model. So there's one thing I want to mention briefly about this, was something that we kind of got for free out of our model. So this is not something that we fit the data on, but a well-known phenomenon in the stellate cells is that they do have these subthreshold oscillations, which is, I guess, part of the reason why this oscillatory interference model is quite popular, because you do see oscillations in the theta rhythm in these cells. So we said, well, can our model do this? Okay, and the point is it does. So here is a spectrogram over sort of a 20-second time period, and you do see a peak around about, well, I guess sort of 8, 9, 10 hertz here. And so this is precisely what the data says it should be, so it's quite happy that our model does this. Hang on. So these oscillations in the actual real cells are thought to be sort of driven by noise, so that's quite happy because the same things are extant in our model. And, oh, right, okay, I just have to give up this really, because this is... And moreover, that we also see this pattern as we approach the transition to spiking, or as we approach the threshold, that we should see an increase in this theta power relative to the broadband power, which again we see here. And this is not that surprising, because when we do a linearization around the hot point before, at the bifurcation point, we see a frequency that is in the theta band. Okay, so essentially what we have is we have a little focus that we're perturbing with noise, so it's not really that surprising that we get power in the right region. So this is where we're up to now with this model here. Actually, the reason why we started to develop these stellate models is to build them into a network model where we could understand the resonances of the whole network. But we kind of, which I thought was going to be a relatively straightforward of picking off-the-shelf models that did this, but then it turned out that there were no models that really did this, so we had to go back and do all of this kind of stuff. So this is just summarizing where we're up to, and then we need to basically do two things here, which is to do simulations of the network to look at how gamma oscillations are nested in theta rhythms, because again, this we see a gradient down the dorsoventral axis of coupling between these two signals, and then of course to go back in and sort of do these experiments where we change the conductance of the AHP, but again that will actually require us to have a bit of better understanding of the neurophysiology of where that is coming from. Okay, so that is the first part of the story. I don't know how long I've taken, but so if there's no questions, I shall move to the next bit and sort of come back to looking at this IH current. So I said before that in terms of dementia models, there was no real observed change in the IH current conductance, but now I'm going to tell a slightly different story which still looks at the IH current, but in a slightly different way. So effectively what these IH currents do is they give you this sort of post-inhibitory rebound phenomenon, because they're channels that activate when the cell is hyperpolarized, and their reversal potential is higher than rest. So if you inhibit the cell for some time to make a sufficient amount of time for the channels to activate, and you release the inhibition, you very often see these so-called rebound spikes. Okay, so here is an experiment here where the cell is being hyperpolarized. When you release it, you get these spikes. And this is due to this, what I call H current. And okay, I said I wouldn't do that, but and there's an idea here that if you do this and you set up networks that basically look like this, where you have stellate cells that project to interneurons and then interneurons that project to other stellate cells, you can generate patterns of firing. And anybody who's looked at central pattern generators are probably familiar with these sort of half-center oscillators. And then if you build up a network of these things, you can get these little waves that go like this. Okay, so these are cells that are now, you can think of this axis as being sort of a physical location of cells and time going in this way. And this will then generate sort of self-sustained waves. And if you think back to the continuous attractor model, this is basically saying the same kind of thing, but posed at a slightly different level. So instead of dealing with firing rates, we're dealing with spiking activity. So again, as the wave moves over, as the rat is moving, we can see activity that would be commensurate with what we record at a specific point in space. Okay, so let's think about a model that does that. And let's throw away everything that we don't really need. And by that I mean we're going to treat this system as being essentially an integrate and fire type model, which essentially just has a leak current, which is basically decay, the IH current to provide the post-inhibitory rebound, and a synaptic current that is dealing with all of the interactions between the stellate cells and interneurons. And what I will say here, and I thank Jürgen for reminding me to say this yesterday, is that the network here is only considering effectively one type of cell, that being the stellate cell, but the projections to interneurons and back again are all encoded in a coupling kernel, which I'll talk about in a second. So although there are no physical interneurons in my model, they are actually there, just provided only by a coupling. And effectively, that then imposes an ideology that these things are behaving linearly. Okay, so because it's integrate and fire type dynamics, okay, we have to be aware that these are spike times, and I put this here only because I want you to remember what TM stands for later in the talk. So effectively, these are just the spike times. And if you compare this model to the continuous attractor model, you can see the same kind of terms coming in. It's just that this is now a spiking model, and this is a firing rate model. And then this is important because this really allows us to tease apart the contribution of the rebound. Okay, so to complete the details of the model, we'll say, okay, so the IH current, as I said before, so it basically is the same as the activating steady state function for the Hodgkin-Huxley formalism, but kind of reversed, because it now activates when it's hyperpolarized. And we take an approximation here that effectively says that the system is piecewise linear. This is not actually essential, but it simplifies the analysis, and it allows us to construct explicit solutions that are exact up to a root find on where the actual firing times occur. So effectively, the red guy here is the normal steady state activation, and we just linearize it to give the blue curve here. In terms of the coupling between, the cells, it's set up like this again. So we have some conductance times a current, and the current basically says, well, there's some weighting between you and your neighbors, which is dependent on the distance between you. So this is the kind of lateral inhibition. And then what you do is you just sum up over some transfer function that tells you how spikes are manifest at the postsynaptic cell. For the coupling kernel, we take something that looks like this. So I said before that what's happening here is we have stellate cells that are projecting to interneurons, and the interneurons are then projecting to another stellate cell. So we consider this to be what we call an inverse top hat function, right? So we're only seeing inhibition in the model. And our synaptic filter function is effectively just an alpha synapse. So it has a rise time and a decay time that are effectively the same. So this is what a cell at some distant position would see when a presynaptic cell fires.
So here the cells are not coupled to excitation at all?
No, so let me go back a sec. So this is the kind of model for coupling. So these guys are the excitatory cells, these guys are the inhibitory cells. So you have excitation from the stellate cell to the interneuron, and then inhibition from that cell to another stellate cell. And this is, broadly speaking, what the connectivity in entorhinal cortex looks like. I mean, there is some excitation, but there's an awful lot of recurrent inhibition in this brain region. But thank you. Okay, so this then basically then completes the details of the model, and effectively all you do then is you say, well, when you're spiking, you look over a sort of disk of some radius, and then basically you integrate this transfer function over time. Okay, so now because the system is linear, we can just write it in this really nice form. So we can sort of go back to our linear algebra theory and say, well, the system basically looks like some matrix A times X, where X is sort of V and the proportion of open IH channels, and then this phi here, psi, sorry, is the interaction with the rest of the network. So all of the coupling is then encoded in this guy here. And if we do that, we can see solutions that look like this. So X is real space. There's periodic boundary conditions here, which is why the thing is going to loop around. So there's some threshold here. So this is an integrating phi type model. So we just append a little spike there. Then the model sits in a refractory zone. Has a refractory period here, and then is released from the refractoriness, and effectively then builds up again and hits a spike. And the reason why I'm showing you this simulation is because this actually is a traveling wave, right? So this is a solution of the model that gives us the traveling wave that we want, because this is what we're saying underlies the grid cell firing. So for a slightly different view of this, you can say again, well, so if I just index my neurons going up like this, and I go in time, so after some initial transient, this thing will settle down into a profile that basically looks like this. So you can either, in one sense, you can view this as a profile over space, and you're moving along where you're looking at it in space, or you can think about it as, well, I'm at a space and time, and I'm looking at how my activity changes over time. Okay, so then the sensible thing to do that is to bring these ideas together, and instead of thinking about yourself as either being fixed in space or fixed in time, you just move to a co-moving frame. So you make the sort of standard traveling wave coordinate transformation, and you look for time-independent solutions, which will give you an orbit that corresponds to a wave, which corresponds to grid cell firing. And effectively what you do is you say, well, I want my wave to be periodic in a sense that after I wait for my refractoriness and my sort of intrinsic dynamics to take place, that I have some delta here which corresponds to my spatial frequency. So delta here is the spatial frequency of the grid cell firing. And then because our system is linear, we have a nice property that, well, so this is true for any kind of system, but our generator for the system basically takes on a really simple form because this is just a set of matrix exponentials. That's shown here. And then all we really need to do then is say, well, look, we've got all of these matrix exponentials. All you need to do is then piece together bits of this thing and just match them at the various transitions. So here is the orbit that I showed you before. So now instead of looking at things in space or time, we're saying here's V and here's NH. So this is my activation of IH. So there are different thresholds for activity. So VR is the reset condition for my IF model. VTH is the threshold, and this is just an artificial spike we put on. And then V plus and V minus are the points at where my linearization of the steady state activation curve for this, where they change. And effectively there's three conditions that we need to impose. So one, that at periods of delta in our traveling wave coordinate, that we are actually at the firing point threshold. Secondly, that, okay, it's not good enough just that V is at V threshold, but also that we really are on a periodic orbit, because this underlines the wave. And also that we have to make sure that we're matching here at the point where our steady state activation curve goes from being flat to being aligned. And so the point is that if we then put together the evolution operator from the previous slide with these three conditions here, we can basically find an orbit. Okay, so that's essentially done. But for those that work a lot in applied mathematics, we know that, well, just finding a solution is not sufficient because you don't know whether that solution is stable or not to, at the very least, to linear perturbations. So this calculation is a little bit involved. So what I'm going to do is I'm going to sort of sketch it out. And if you want to know more, then we can talk about it later, I guess. So the idea is that what we're going to do is, rather than the sort of standard applied mathematics thing, where you have some sort of PDE and you write down a profile, we're going to start from somewhere slightly different, and we're going to say, well, let's perturb where we hit threshold. So imagine you've got now a nice wave going along, and then you just slightly wiggle where you hit that threshold in terms of your wave coordinate. And then the question you have to answer is, well, how does that change the profile? And the answer is, well, it changes the profile through changing where you get synaptic input, because otherwise the system is just basically just decaying to zero. And actually what you're doing is you're changing this psi. So this psi here is the traveling wave synaptic input, and then essentially we perturb firing times, or threshold crossing events I should say, and then this leads to perturbations in synaptic drive. And it kind of does it like this. So we have a nice relationship here that says, well, if we look at sort of Dirac deltas of functions that take on zero at certain points, then we can relate this to those Dirac deltas of those points scaled by effectively the magnitude of our voltage variable at that particular point. Sorry, time derivative, I should say. And we can do this exactly for the wave. So this is basically the same equation now, but written in terms of our traveling wave coordinate. And then you might think, well, how does that help you, right? Because it's not clear that this has anything to do with what we're talking about. But if we re-express the synaptic input we get, remembering that now that we're looking effectively at our wave coordinate, we can just express this as picking up contributions only from cells that have hit that threshold. Okay, so there is a Dirac delta here. And if we substitute in this guy here, this formula, then we can express this like this. And then we can use the second of these to express this in terms of our traveling wave coordinate. And then, and this is the bit that I'm not going to show you because it's not super long, but it's not very exciting to look at, you can then compare the unperturbed and perturbed case, and by perturbed I mean ones that have different firing rates, different firing thresholds, and you can basically show that you can express the perturbation to the synaptic drive by just basically subtracting this guy from the unperturbed case, and you get a relationship that looks like this. Okay, so and effectively what's happened here is you've used the Dirac delta to just pick out certain points of W, and the idea is here that all you're really doing is you're integrating over your derivative of the coupling kernel. Okay, so there's some slight technicality when you do these kind of calculations because it's an integrate and fire model. And I actually think this is quite important because until very recently there's been a lot of studies that haven't quite applied them in the correct way. And the idea is here that because you have a system that is going through a discontinuity, a real discontinuity, a hard reset, you have to be really careful about what happens to perturbations as you go through that discontinuity. And so you can demonstrate that you can express perturbations in your threshold crossings with respect to, again, temporal derivatives of V and the perturbation in V. And then this allows you then to essentially rewrite your perturbation to your synaptic drive as a function that we defined earlier, just scaled by this point, by this voltage operator. But importantly, this is evaluated at the point where you cross threshold, which is equivalently at xi equals 0 or delta. Okay, and then, so this now is the perturbation to psi. The rest of the equation is quite simple because if you just ignore this bit here, you just have a linear system, okay, and we can all solve linear systems quite easily. So the variational problem is effectively just a linear system plus, this slightly more involved bit here, which we've just derived. And then the final thing is to recall that actually, these threshold events are not just when we hit the reset, but also when we switch between the different linearizations of our steady state activation curve, and also when we come out, we exit this refractory period. But nicely, and if you're interested in learning about discontinuous dynamical systems, there's a great book here by Filipov. Effectively, what you do is you write down something called a saltation matrix, where you first look at what the difference in time between when you would hit these various different manifolds is, and then you express that as perturbations in whatever your variable of interest is, so here V. And the point is then what you end up with is a an equation or a matrix system that tells you how perturbations before you hit some threshold are related to perturbations after you hit that same threshold. Okay, and this is not super important, but the point is they all have relatively nice forms. And again, unsurprisingly, what they look like is they look like evaluating temporal derivatives of your variables at these different thresholds. And finally, we put all this together, and what we end up with is we say, well, okay, let's consider one period of our orbit, and we get some function here called gamma, which relates eigenvalues around our linearization to the period, or the wave period, delta. And I put this up here not because I really want you to remember this formula, but just to show you that it depends partially on the variational problem and partially on these saltation matrices that we just talked about. And then what you can do is this then gives you a complex valued function, the roots of which are basically the spectrum around your wave. So what you can do is you can say, well, I'm going to go find all of these different roots, and you can say, well, the wave is stable if all of the real parts of my eigenvalues are in the left-hand complex plane, except for this one guy here, which is basically just a translational invariance property. So here we have a stable solution, and here we have an unstable solution. And then you can trace out regions of stability in the system. So here we vary two parameters, one of which I'll talk a little bit more about in a second, and essentially the strength of coupling between the two cells. So blue here is stable, green here is unstable, and what I mean by that is that we've just tracked the first pair of complex conjugate eigenvalues to cross over the imaginary axis. Okay, so the point is that there's a big region here in which you're stable. And now the interesting thing about this, particularly in the left-hand diagram, is so you fix a tau h here, and you look at this whole region here. This is delta. This is the wave period, which is then related to the grid cell spacing. And the point is that you have a whole region of different wave periods that are stable. So this kind of looks like this. So the bold line here are stable solutions, the dashed line are unstable solutions, and the red is just when this first complex pair cross. But the point is that what you have is you have a dispersion curve which relates the speed of the wave to its wavelength. And the speed, I mean, we don't really care so much about. This is the key parameter for us in terms of matching the data. And you have a whole family of solutions that can exist. And moreover, you can control the width of this by varying not the conductance of the IH channel, but the timescale of the IH channel. Okay, so this, basically the gating variable follows a Hodgkin-Huxley formalism. So it has a timescale, and if we vary this, we can vary the extent of grid cell firings that we can see. And importantly, this does not require any changes to the coupling, either in terms of the spacing of lateral inhibition or in terms of the strength. So this is an intrinsic property that is setting the grid cell spacing. And this is kind of why I think it's a really interesting thing, right? Because we've achieved what we wanted to do, but without kind of, not cheating, but putting in what we wanted to get out. So that analysis is all in 1D. This is a simulation of these things in 2D. It's not quite necessarily what I want, because you can see the effect of some boundary conditions as the simulation goes on. And nor have we extended yet this analysis to 2D, which of course is the natural framework for looking at these things if I'm imagining that I'm moving around a planar environment. But really, what I want you to focus on is that you can see already, even though this simulation isn't quite set up correctly, and because we haven't done the 2D theory, we don't know what the parameters are that we need to fix here. But you can see, at least locally, these hexagonal patterns that basically correspond exactly to this kind of continuous attractor kind of model where you have waves that are propagating over a bit of neural tissue. So, the next thing to do is to really get a handle on really how to analyze this system in 2D. So establishing where these patterns are is quite easy, but their stability calculation gets really hard because you've now got a whole other direction in which you become unstable. So just to summarize this bit then, so effectively we've considered a really simple model of rebound firing with a coupling kernel that essentially matches the physiology of the entorhinal cortex, and effectively shown that this is sufficient to generate waves, calculated exact solutions for it, but also that we can control the grid cell spacing by controlling intrinsic cell parameters and not coupling parameters. And then, as I said, now we have to go through the gargantuan calculation for 2D. I just want to end by thanking all of the people that I worked with on this, including Krasi, who's sitting over there, and of course, so the people that funded me throughout this, the Medical Research Council and the Wellcome Trust in the UK. And yeah, thanks for bearing with me.
Probably we should move on without too much question to try to finish on time. And then there is a burning question that wasn't asked during the talk. Okay, so let's thank Kyle again. So the last speaker is Jürgen. So it's a pleasure to have Jürgen Reingruber. Jürgen
didn't learn to express my name correctly. Reingruber.
Okay, thanks for this clarification. So Jürgen is working on transduction, phototransduction, and recently he has been interested in olfactory receptor and olfactory transduction. And so he's currently working in my group in Paris, but on this particular topic. We are very happy to have you here, Jürgen.
Thanks, David, for this nice introduction. Thanks to the organizers for inviting me. So, yeah, this is about sensory transduction in vertebral olfactory receptor neurons, and it's also, like the two talks before, a nice example that shows how mathematical modeling can lead to some conclusions that are otherwise very difficult to get experimentally. And so it's also a lot about electrodiffusion, so it's similar to what Thibault already. It's probably a little bit more complementary in some sense, you will see. So the outline will give you a biological motivation, then I will show you the spatio-temporal model, electrodiffusion model, and I show some simulation results and the conclusions. I try to be fast so that we are not starving too much. Okay, so what are sensory neurons? Basically, sensory neurons are the first neurons that get activated by a stimulus. For example, there are rod and cone photoreceptors in the retina. Here there are olfactory receptor neurons in the nose, in the epithelium in the nose, and this is hair cell bundles. And so basically, as you can imagine, these neurons are fundamental because they are basically our window to the outside world. And so a question in this part of sensory transduction is, okay, if you look at them, they all have very different shapes, and if you look at the signaling pathway, it always involves different proteins. So one of the basic questions, how does the signaling pathway, then the cell structure, and the ion dynamics in these little tiny structures really determine the neuronal response? And so I analyze this in phototransduction and here in olfactory receptor neurons. And here, so just to give you a brief introduction to biology, here you can see the head of a mouse, which is cut in the middle, and so here you can see this is the olfactory epithelium in the nose. Basically, this is the here what you have in the thing in the nose, the layer here, and here in this olfactory epithelium, there's this is the cilia. This is basically the inside of the nose, and here this is the boundary. So where you can see there are olfactory receptor neurons. They project there, and they have the cilia. They are on this kind of mucus there, and here is where olfactory proteins that you inhale via air, they bind to some receptors on the surface of the cilia, and then they introduce a signaling cascade, and then which leads to a depolarization and spiking of these neurons. And so what is really in olfaction is really, so you have, let's say, 300-400 different types of these olfactory neurons, and each one expresses a different type of receptor. So they are distinguished by the type of receptor they express. And so each receptor is somehow susceptible to different set of chemicals. And so basically if you smell garlic or something, so the accumulating effect of all the receptors that are activated by these things what makes up a garlic smell, they really then they determine in the brain and the sense of smell. And so what you can see also here, you have, let's say I said you have 300-400 different types of receptors in the nose, and they're each a neuron, and they project, what is also interesting, each neuron that expresses a particular type of receptor, they project to the same structure, which is called glomeruli. So each neuron that have one with respect to this glomeruli, the second neuron projects another glomeruli. So basically there's a lot of integration happening already here on this layer. But my talk will be basically about what happens now in the initial part here, where the olfactory, the odorant molecules, they bind to receptors and initiate the cascade. So, so here you can see now this olfactory receptor neuron. This is a staining. You can see that here is a cell body, there's a dendrite, and here is basically the olfactory epithelium in the nose. This is here is a bulb, and here of this bulb, usually you can see this, you don't see it here, the staining, but this would come out here of this bulb. And this is basically this lives in the mucus in your nose. And basically here is where then when you inhale, then the odorant molecules, they bind to these receptors here. So you see that they have a specific shape, and what I will now discuss more is what happens inside this cilia, which is here where the signaling pathway is initiated. And so here there's an olfactory signal transduction pathway. So here you can see a schematic of such an olfactory receptor neuron. This is the nasal cavity with the cilia embedded in the mucus. There's here then the dendrite that goes to the cell body, and then it projects to the synapse. There are spiking neurons. And so here what happens now when your odorant is inhaled, it binds to receptors on the surface of these cilia here. Then this activates the receptor, then this receptor activates a G protein, and this G protein activates a cyclase, and this cyclase now generates cyclic AMP out of ATP, and this cyclic AMP, which is really particular of this kind of factor receptors, that opens first CNG gated channels, that this influx of sodium and calcium, which is very important, and then this calcium influx activates another type of channels, which is a chloride channel. So basically the calcium triggers the opening of these chloride channels, and I will show you later this is actually the main amplification step. And also what is important here for later on, there's also an exchanger, there's sodium-potassium-calcium exchanger that really then, because calcium flows in, that is really responsible to extrude calcium, and this is important for response termination. This is in brief the signal transduction pathway. What is important is that you have two different types of channels. One channel that is permeable to anions, that is really what is anions? Is the positive ones or anions or cations? Huh? So the cations. So there's a permeable to cations, and this is gated by cyclic AMP, and the other one is permeable to anions, which is and the chloride flows out. So basically here you have positive flows in, negative flows, so it's both depolarizing current. So they're both this kind of thing, they depolarize the cell. And so here I show you quickly, so this is now some experimental results from my collaborator with him did the project, Johannes Reiser from Monell Institute. You can see here that you have, so this is the normal, so when you just give a brief pulse, you activate the cell, you can see this is the current that you get. This is via suction electrode recordings. And then you block the chloride channels. And this is the red curve when you give the same pulse, but you block the chloride, you see that the current is much reduced. You can see that most part of the current is due to these chloride channels. And here is now, if you, for example, completely knock out the chloride channels, so then of course, this is blocked by some pharmacological stuff. So you can see if you block if you don't have the channels, nothing happens, even if you block something. And here this is another experimental recording by Menini in Boccaccio from Italy, and where you can see, okay, if you now inhibit the chloride channels, the current, this is the normal current, and this is much reduced if you inhibit the chloride channel. So basically what is shown that this chloride current is the major amplification step, and there are also many more chloride channels compared to CNG channels. And so what people were puzzled since now, let's say 25 years, is why you need a chloride current. Why is it, for example, that's not all done by what is in general think by sodium current? And so what is the role of this mysterious chloride current, which is because in most other neurons they really just rely on a sodium current. And so one of my ideas was, okay, maybe this has to do with the ion dynamics in such small spaces that are there. So maybe this is different with the chloride compared to a sodium current. And so basically if you look, the cilia here, they have a volume around 0.5 femtoliter. They are 25 micrometer long, around 150 nanometers wide. And if you now look at this volume, you compare what is one molecule or one ion in such a volume already leads to a concentration of around 3.4 nanomolar. So if you have 1,000 ions, you can see that's already micromolar concentration. Then if you look at the current, that if you assume that current that flows into this, if you have a current of 1 picoamps, that can change the concentration with 20 millimolar per second. The second should be down actually here. So you can see that even a small current, the currents here typically can be hundreds of picoamps. You can see even these currents, they can quickly in millisecond timescale change the concentration here by a really important thing. And then, for example, you can also look at now the capacitance. You can see the current. You can see that, for example, 1 picoamp current leads to a change of 7.2 millivolt per millisecond. So you can see that even small currents in such small spaces can really very quickly change concentrations and voltages. So one of these, okay, so now maybe there's a difference if the current is carried by sodium or by chloride. This was the idea. It's okay, of course, to test this. And you can imagine it's very difficult to test this experimentally because you cannot simply change the conductance of a channels from sodium to chloride or add more other different types of channels. You completely mess up. So it's a question that is very difficult to study experimentally, but you can use it and study it with a model. And this is exactly what I did. So first you have to get a spatio-temporal model. So basically you have here a cilia, which is approximated as a 1D cylinder. You have to put all different players. You have to put cycling AMP. And Thibault this morning also had a positive or negative ions, but here we have 4 different types of ion. You have chloride, of course you need sodium, of course you need calcium, and I also added potassium here. So then, because you want to study the difference between sodium and chloride, you have to have at least these 3. But you will see also potassium plays an important role actually, although there are no channels for potassium there. Then of course you need the 2 types of channels, the CNG channel and the NO2 channel. The one is, and then you of course you need an exchanger. There's a sodium potassium calcium exchanger. So basically it works like this. So basically sodium flows in and the potassium and calcium is extruded. So the sodium driving force really drives this exchanger. Then here this is all time dependent. It's in the cilium. Then here in the mucus I assume that the potential concentrations are constant because the space is much bigger, but this is now a first simplification, so later on you can relax this, and then you need to couple this to a model for the cell body. And here I also use a very simple model where I assume that the concentration are constant here, and there's only a leak term that generates basically a steady state of the cell body potential. And then, but the cell body voltage in general is time dependent, depends on the current that is generated here through the channel that flows through this. So basically this is the framework of the model. Now I'll show you quickly the equations. So basically what I do, because it's a cylinder, so I just use normalized quantities. So basically this is the normalized length. You just divide by the length of the cylinder. You just like Thibault did this morning, you just generate a normalized potential, which is just the potential divided by this thermal value, which is 25 millivolt. And then you can also get, now you have currents flowing from the mucus via the membrane into the cilia, which is membrane currents. This is basically usually the thing which is mole per micrometer squared per second. So you can also now renormalize this via the radius because you have cylinder. So you get a somehow modified current, membrane current, and you can also use the normal longitudinal flux, the Nernst flux, so which has the diffusion term, and you have the drift term due to the potential. And if you do use this quality, you just have this diffusional timescale, which is just given by d over L squared. This is basically the long what Thibault talked to this morning. This is a very slow timescale due to the diffusion. And so basically here, if you do this rescaling of these 2 fluxes, you can see that these fluxes have a unit millimolar or molar per second, which is very convenient because it allows you much more to see, okay, if you have a flux that flows in like 1 millimolar per second, you know in 1 second it would change the concentration by 1 millimolar. This is much more interesting than if you would have now molar per second to see what's actually happening, how the concentrations are really changed inside the cilia. So it's more intuitive to work with these fluxes than with some normal fluxes like these ones that have molar per micrometer square per second. Okay, and so now you get the normal Nernst-Planck equation where the concentration inside the cilia, S stands for the different species. they change depending on, this is the longitudinal flux, and this is the flux that flows in via the membrane, which depends on the opening of the channels and odorant activation or whatever you see later on. Okay, this is the thing, and then you need equation for the ciliary potential. Here you can see this is basically the connection between the current and the fluxes. Here this is the current via the ciliary current, the longitudinal current. This is the current via that flows in through the membrane. So basically you use what also Thibault used, the charge capacitor relation. We say the change in the potential is just given by the currents that flow in. So the current that flow into the segment and divided by the membrane capacitance. This is basically the same like Thibault. This is also basically it's also the cable equation. If you assume that the concentration current, this is the same format like a cable equation. But here the concentrations are not constant, but the form of the equation is the same. So basically what you can assume, of course, this is related to the change in the concentration, so you can write the same equation like this, where this is what I think Thibault had this morning, where you can see that the change in potential is related to the change of the total charge in some segment divided by the membrane capacitance. So, as I said, I didn't use the Poisson equation here because this framework is much easier to solve, and I think the Poisson equation doesn't give very much different results that I will present you here. So then you need another equation for the cell body potential. Is the same. As I said, you have a leak term, is the cell body capacitance, and you have then it changes due to the current that flows in from the cilia. And here we have n, it's like in the simulation we have 15, you have, because there were many cilia, around 15 cilia, and so basically all of them, I assume that they are all activated the same way. So basically then the cell body changes due to this number of cilia times the current from one cilia. But here I assume that I don't make any difference in the activation of the cilia, so they're all activated the same way. Then you need the fluxes between the cilium and the mucus via the two channels that are activated. And so basically here I use the Goldman-Hodgkin-Katz equation like Thibault, but he used the linearized form here. I plug in, since I don't do any analysis here, you can use basically the full form. It doesn't make any difference for the simulations to use this. So, and here it depends really what is interesting here, what is the captures main features of the system, so that the current depends on the concentration inside and outside, and onto the voltage difference between inside and outside. And then you have here again some kind of the open probability of the channels, and you have here the conductance of these channels, which depends basically on the single channel conductance and the density. This is some rates, and this is the open channel probability. And now look at, this is generic, these are both types of channels. Just then for the NO2 channels, they are activated by calcium. So basically here the open probability depends on the ciliary calcium concentrations. Here's some kind of function, so a Hill equation. And then you have the channels that are activated by cyclic AMP, and they depend on the cyclic AMP concentration. And also what is, it's important that there's negative calcium feedback on these, so they are deactivated by increasing calcium concentrations, which here are incorporated by changing this kind of Manson constant. So basically this increases if the calcium concentration is increasing by some rate f, which is somehow 4 to 5. And so then what you need also the exchangers, because the exchangers extrude calcium, they're important for deactivation. So basically these exchangers, they, as I said, there are 4 sodium that flow in, and then 1 calcium and 1 potassium flows out. So basically, okay, if you count this is not 0. So the exchanger is electrogenic, so it generates a current. This is the current that is generated by the exchanger. This is basically the flux. So if you sum this up, you need, this is the flux, for example, of either potassium or calcium. And so basically what you need an expression for this flux. And so here I generalize the formula for the NCK exchanger, sodium-potassium exchanger to sodium-potassium-calcium exchanger. And so here basically what is, you see it depends on the, again it depends on the concentration difference between the cilia and the mucus, as you would expect, and on the potential difference between cilia and mucus. And there are only 2 parameters here, 3 parameters, which is the rate, and which is here some kind of Michaelis constant for calcium. And so you can rewrite this with some kind of Nernst potential. You can use the Nernst potential, and you can see that, okay, what's important to check just that you do everything right, that for example the exchanger flux vanishes when the free energy change is 0. Basically when if you introduce 4 sodium introduce, you have the kind of, this is the nonce potential, so the energy change is 0. So then it's basically the exchange of flux vanishes. But also important. So basically, but what is important here that you have an expression where the exchanger really can go in both directions. If you look at this, it's completely symmetric between cilia and mucus. So there's no, so this is a, so the exchanger could go in forward or reverse mode. And so basically here you can now take this expression that I showed you before, and you can assume in the physiological range where the concentration are such that this is large compared to this, then so this term already dominates, and then you get what usually people use in their formula, where just the exchanger depends on the calcium concentration in the cilia with some Manton term. But if you use this kind of equation, which I did a long time, you don't find really interesting effect because the exchanger cannot go in the reverse direction. So here you get a completely different dynamic. You get the dynamics right in the physiological range, but if you perturb it, you don't get it right. And so then you have also to have the signal transduction, which is for the activation of cycling AMP. You have some odorant that bind, and then they activate the receptor. So as he assumed, because this is the activation is fast, so assume that this is a steady state. So basically for a given odorant concentration, this is a steady state concentration of activated receptors in the membrane. And then you start to activate the G proteins, the odorant receptor, and then you have deactivation rate. The G proteins activate the cyclase. Here you can see this is the activation, and you have a deactivation constant. And then this cyclase then activates cyclic AMP. This produces cyclic A with this rate. Then you have diffusion of cyclic AMP in the cilia, and this is a degradation of cyclic AMP. And here there's again, also in this case, there's negative calcium feedback on the synthesis of cyclic AMP, so which you can also now increase by having this kind of parameter F that really increases when the calcium concentration is large. This is usually more complicated, but here this is really a simple manifestation. It doesn't really change the main conclusion that I will present. And so, okay, so then you have everything inside, so then you need a boundary condition in the cilia. So first of all, at the tip, it's a closed end, so there, of course, you have no flux boundary conditions. And the question is, okay, what happens here, where all the cilia flow into this dendrite? And so here you could now assume, okay, so either Dirichlet boundary conditions, but since there are many cilia and this is not so much bigger, you can imagine that the concentration not necessarily will be constant here. So basically I chose to flux boundary condition. So I assume that, okay, at this tip, the flux between the such cilia and later on the cell body here, it goes through the dendrite, is something like a Goldman-Hodgkin-Katz equation. It depends on the concentration in the cilia, at the end of the cilia, and the concentration that you have in the cell body. Remember, this is constant that they use. And so then you have this kind of, this is an assumption that I use here. This is form of the flux, but it has some kind of qualitative features that are right. So basically the flux that you assume that flows here depends on the concentration differences, and it depends also on the voltage difference between cell body and here the cilia. So it captures some main features, and then there's of course some parameter alpha, some rate, which is the diffusion rate like before, and then some parameter alpha that really you could say, okay, you could vary this. For example, if you let alpha go to infinity, you would get Dirichlet boundary conditions. So now, depending on alpha, this could capture, for example, some kind of geometric features or some kind of hindrance, whatever, that really modulates the flux between the cilia and the cell body.
Jürgen?
Yes?
So here you're considering the influx of all the cilia to get the concentration of the cell body? Or you linearize, you say that
the cell body concentration are constant.
They're constant?
Yeah.
Okay.
This is here, this is constant. And so okay, so this is the stuff. And then what is also very nice from this, because many parameters are not, as you see, I have a complex model, a lot of parameters, so many parameters are not known. So I wanted to really now adapt the model to some experimental measurements. And so it's very hard if you have now a coupled system of PDEs with everything to really fit this to experimental data. But if you have now these flux boundary conditions, it's very easy to generate a well-steered model. You basically replace this here, the divergence of the flux inside the cilia with the flux between cilia and cell body. And this, I already have the expression, that is what it has a boundary condition. So basically, this naturally reduces to a well-steered model. And I will use this well-steered model to really to get some parameters that work, and then I use these parameters into my spatial model again to do simulations. Basically, this is, now I'll show you here. Okay, so, and yeah, okay, so, and remember the question was, okay, why chloride current? So the thing is, what I did now, okay, you have in one scenario a chloride scenario. You assume that these NO2 channels are permeable to chloride. So if they open, chloride flows out. Then you compare it in a completely artificial situation. That's why this is very hard to do experimentally. But with a model, you can do it. You just assume that these channels are not permeable to chloride, but they are permeable to sodium. So basically, when the calcium activates channel, sodium flows in. So then you have two different situations, and you compare what is actually the difference in the outcome of the concentration here. So basically, what I will show you now, everything is the same, just between the two, and just the permeability of this channel. In one case, it's open to chloride, in another case, it's open to sodium. But the rest is everything, parameters are all the same, what I will show you next. So this is what makes it very easy to compare. Yes.
Channel permeable to sodium, are you also changing the reversal potential? Or are you only changing which ion concentrations are affected?
I only change the permeability, but the reversal potential is determined by the concentrations between the mucus and this. So this I don't change, don't affect it. So the concentrations remain the same. And
so it'll have the same electrical effect, but it'll have a different ionic effect.
Yeah, you just change the conductance to this, but the reversal potential are determined by the concentration, which are not changed. This is the stuff. I don't know if this was
no, but I think that because you change the species, that will change your reversal potential effectively. Because
it will change the dynamics and stuff.
But not the function. Yeah, it will be the same formulation. It just will change it otherwise. So I think you're both right. You're saying the same thing, but
basically what you do here, you see, this is the channel here. Oops. Oh shit. Sorry. Here you see. Oh, where is this now? Okay. Somehow it's complicated here.
But isn't your reversal potential depend on the species?
Everything the same. You just change this is, for example, in the NO2 channel, this is probability, this open. This is just either, this is the conductance. So you just change this parameter. The rest remains everything the same. Just change this. For example, this NO2 channel, this is 0 for all ion species except for chloride. And in this other case, you make this 0 for chloride and make this non-zero for sodium. Only this parameter that is.
But what about the dependence on the ion concentrations?
This is the same. It remains the same. You just change the conductance.
But your ions are different now because you are flowing their sodium rather than potassium. Oh, well, not potassium, but chloride.
Yeah, now sodium flows in.
So it will be different term there for the ion concentrations.
No, this is the same. This is the ion concentration S. This is now for sodium, whatever. So this is, for example, in chloride, this is non-zero for chloride. And then you have the chloride. It depends on the chloride concentrations.
And then when you have sodium, it will depend on the sodium concentration.
Yes, because this is S
so
here.
It will be changing. Yeah, that's all right.
Yeah, clear. Yes, clear. You don't have a sodium flux that depends on the chlorine concentration. Yeah.
Exactly.
Okay. So this is the thing. So basically, you have now well-defined two scenarios. Everything the same, just the conductance of this channel. And so now what I did, I calibrate the model to experimental data from my collaborator, where we have 1 second stimulation here, O-turn stimulation for 1 second, and in 1 second it switches off at different concentrations, 3 different concentrations. So now I used the well-steered model to fit these two, the wiggled line experimental data in the chloride and the sodium scenario. So basically, but remember, there's only one parameter that is different. So everything is the same. Only one parameter is different between these two simulations. So you can see that in principle, I use the D2D framework here. In principle, you can, what it tells you, you can fit, if you just look at the current, you can fit your current equally well with the sodium or with a chloride current. So nothing is different. So in principle, if you just enter the curve, you say, it works equally well with the sodium with chloride. And so then, but now what I did, so now this is now the well-steered model, and I use the same parameter inserted into my spatial model. Of course, it's not anymore as perfect as before, but it's reasonably well. It still gives a reasonably well approximation of the thing, which was already sufficient for me because it just gives you the right it gives you the right framework. So you have parameters that work well. So again, here you would say, if you look at this, I don't see any much difference whether you do it with chloride or sodium. The thing. And so you look, for example, at the dynamics of standard variables that are used for some olfactory responses up to now, which is usually they assume that the concentration are constant, except of the calcium concentration, of course, and the cyclin B concentration. So basically, if you look at the cyclin B concentration, calcium concentration, here's the cilia voltage or the cell body voltage, you don't see really a big difference between both scenarios. So if you would have such a model, you would say, okay, it doesn't make any difference who carries the current. This is what you would expect also from a cable model. In a cable model, it doesn't make any difference whether the current is carried by chloride or by sodium. But now you can look at what are the other, for chloride and the sodium concentration. Here now you start to seeing big differences between the two scenarios. So the solid lines are with the chloride current and the dashed lines are with the potassium currents. As you can see, for example, if you have a chloride outflux, the chloride concentration this is averaged over I will show you the gradients in a second, but this is the average concentration. You can see that, of course, because chloride flows out, the concentration in the cilia goes down. And you can see that the sodium concentration is almost not affected in this scenario, in the chloride scenario. And you can see also because of what Thibault talked, because of the ciliar depolarization, potassium is driven out of the cilia. So you have although you don't have potassium channels, the potassium concentration considerably increases and is driven out of the cilia. This is very important to basically maintain electron neutrality in the thing. So now you look, okay, now what happens with the sodium current? In the sodium current, you can see what is, of course, because now sodium flows in, you can see that you have a huge increase of the sodium concentration in the cilia. Now, again, because of the depolarization, chloride is sucked into the cilia, so the chloride concentration now increases instead of decreasing, and the potassium concentration still, it's the same, it decreases, but a little bit stronger.
I have a question. If you don't have chloride coming in through the channel, where does it come from in your sodium scenario?
From the cell body.
Oh, okay, but you're having it in the cell body at some constant, like whatever experimentally is known. I see. Okay.
With that 80 millimolar, basically. This is the steady state in the cell body, which is because this determines also then at the cilia. If you don't have any opening, the cell body determines what happens in the cilia.
And is it the case when you have your chloride scenario in the cilia, you don't have any sodium fluxes? All the sodium would be coming from the cell body again.
Yes.
Yeah. Okay.
But as you see, with the chloride current, the sodium is almost not affected. It's just because potassium does all the work here. That's why it's important to have this potassium which equilibrates the chloride. There's two. And I have to say, in principle, you could also add anions, proteins, large proteins here, but I didn't add them here because I assume that they are immobile. But for the dynamics, if you add these immobile ions, it wouldn't change anything for the dynamics because they are. But in principle, for example, if you add all of this concentration, this is not electron neutral because you have to add also the rest for the anions. But I assume that these anions the diffusion is very slow, so they don't contribute to the dynamics here. And then you can see, for example, now you look what is the osmotic concentration change? You can see now if you have a chloride current, the total, if you sum up all the ions in the cilia, it decreases, whereas with the sodium current it would increase. So now you can say, okay, would this have an impact? I don't know, but at least since this is a proportion to the osmotic pressure, you could assume that if with the sodium current, you would have an increase in the osmotic pressure. For example, if you use Van 't Hoff law, you can see that for 1 millimolar solution, you would get a change by 25 millibars. So now if you assume you have 40 millimolar change, you can assume that this starts to become maybe an issue for the cilia. I mean, in the water case, the cilia would probably, in this case, you would water outflux, so they will fall a little bit, become shrinked, but in the other case, they could burst in this case, because water would try to flow in. So this could be an issue. And then you can look, okay, of the spatial distribution. You can say here, with the chloride scenarios, sodium remains more or less stable, which is important. Remember, sodium is the main driving force for the exchanger. So with the chloride outflux, the sodium concentration is almost not affected. But if you have now sodium influx in the other scenario, you can see that the sodium concentration in the cilia can reach very high values. It goes from at steady state it's 4 millimolar, it goes up to 60, which is huge. And this starts to really, then you will show later on, it starts to affect the exchanger, affect calcium extrusion. And then you can see again the chloride concentration in one scenario, in the chloride scenario it goes down, in the other scenario it goes up. You can see this is the concentration profile. The potassium concentration you can see here, of course, in both cases they are going down. You have this kind of profile. And you can see also the ciliary voltage. As I said, this is not so much different because, as I said, you can, if you just look at the voltage, the current, you can fit it with both sodium or chloride. So there's not a qualitative change in these two things. But here, there's a big change in these two ions. Yes, what is then now, okay, when you look at, okay, what happens now if you assume that the concentrations in the mucus, because the mucus is something that you inhale if you go swimming or whatever, or you have a cold, you can assume that maybe the composition of your nose changes. For example, if you sneeze your nose, it might be different after than before. So okay, what is if you smell and you change the concentrations of the mucous environment? Basically, you change the concentration of chloride and sodium in the mucus. And so basically you can see if you have a chloride scenario, here you can different simulation where you change the concentration of chloride and sodium in the mucus from 140 to 170. 140 is a Ringer solution, this is what experiments were done. You can see that basically it doesn't change the response. This is something, it's also because chloride flows out. And because if you change the mucus, it doesn't affect really when something, the chloride outflows. In contrast now, if you look at the sodium, you can see here if you change the mucus concentration you have a big difference, basically because now sodium flows in from the mucus. If you now change the concentration by a factor of 2, the current goes down by a factor of 2. But also what happens here, at some point you can see here again there's 1 second simulation. At some point here at 70 millimolar, if you go down, the current doesn't go anymore to 0. So basically you have a bifurcation here. Basically here now you get to a second steady state that is appearing. This second steady state is due to the fact that now here you can see the concentration. This is for 70 millimolar. You can see the concentrations of calcium go up, chloride here, everything. So now what happens actually here, that the sodium concentration reaches such high values that the exchanger in the frontal part switch to reverse mode. So can you hear? Here's the influx. The influx of calcium, you can see it's positive, which means that calcium is extruded. But now you can see at 2 seconds it is unsteady. So you can see that now in this frontal part, this is the position between 0 and 1. This is the tip, and this is the interface with the dendrite. You can see that in this part here, 0, the exchangers switch to reverse mode. So basically they intrude calcium. And because calcium activates the channels, you can have a steady state even without odorant activation. So basically the initial odorant activation to push the system over the separatrix, and then once it pushes the system, it goes to the basin of attraction of the second fixed point, which is basically you completely abolish the response terminations. So basically the system is, with the sodium current, the system is not robust against changes in the mucosal ion concentrations. And so what is also see, you can do now the same simulation with the well-steered model, what usually is used, and you can see you don't see this kind of bistability anymore. So basically here another analysis would have to be done to see whether you simply don't push the system over the separatrix or whether the second fixed point is completely gone. So I don't know. But you can see that this bistability really depends on this diffusion or spatial properties. For example, here that in the frontal part of the cilia, the exchangers switch to reverse mode, whereas in the latter part they are in normal, they extrude calcium, but here they intrude. So it shows you that it depends on the geometry and on diffusional properties, the result. And so you can also show, for example, what is a simulation just to show what is the impact of the potassium concentration. Assume that you would put the potassium concentration, keep it constant. You can easily keep it constant by assuming that the diffusion is 0. So you can see here, this is the one simulation. The one is with potassium dynamic, and the other one, the dashed line, with potassium that is kept constant. You can see again, if you just look at the current, it doesn't really make a big difference. So, but if you now look at, for example, at the concentrations of chloride, so now this is when in the scenario you can see that in the one when potassium is dynamic, it goes down, whereas when potassium is kept constant, the chlorine concentration does not change anymore. because it cannot, because potassium, it can only change because there's nothing to compensate. So because of this, due to electron neutrality condition, the keep forcing potassium constant also forces the chloride more or less to be constant. And here you can see is what is this? This is the sodium concentration. In the chloride scenario, it doesn't really change that much. And here you can see now this is the simulation for the sodium scenario. You can see if potassium is constant, the chloride concentration even goes to larger values, increase more strongly simply in order to compensate, because now potassium is not anymore there. A decrease in potassium to compensate for the influx of sodium. So now this has to be compensated by influx of chloride. So you can see now here that the ion dynamics is really strongly coupled. So it's not that keeping the potassium concentration, saying I do a model potassium, there are no potassium channel, I just keep the potassium out of my equations. It changes the dynamics of the other ions in such a small thing. Then what is also then you can say, okay, what if you now increase tenfold the radius? And then you can see, for example, now here, of course, because the radius is increased, the surface is increased, so you have many more channels, you increase the current. So I didn't change anything, just the radius I increased. So, but of course, you get much more current because simply the surface is tenfold larger. But even with now, let's say, 5 times higher current, you can see that the concentration changes are very little. So you can see that now in this scenario, where it's the same now, the cilia would become to the size of an axon. A cable model where you can assume that the concentration are constant would be a valid approximation compared to this. So now to conclude, I showed you that there's a big difference between sodium and chloride current, although they are both depolarizing currents, but there's a big difference with what ion species carries the current because of such small spaces that you have. And then the sodium current induces large sodium fluctuation in the cilia. Then there is not robust against concentration fluctuation in mucus. Then this also, because this large concentration, this affects the exchangers, which if you would have calcium activated sodium currents, you would get bistability, and it would also increase the osmotic pressure. Actually, it's interesting, if I looked in the literature whether there are calcium activated sodium channels, and I only found 1 or 2 papers, and they apparently exist in some egg where they induce long lasting action potential apparently, but if not, they are almost not absent, and maybe this would be one of the reasons why they are not there, because most of the time calcium extrusion is done by exchangers that are driven by the sodium channels, and this could be a mechanism why they are not so widespread, because if you have this, you get a positive feedback loop, and so basically you could at some point auto-activate the system due to this bistability that is there if you have a calcium activated sodium channels. Okay, thank you, that's it.
Can I ask you one question, just very quick? So you have the chloride channels everywhere. I mean, I appreciate that he showed that in small, in small spaces, in small compartments, they might be important in that way. But they are also in big compartments. But then you said that doesn't matter. Did I understand correctly? Whether we substitute them with sodium or not when you are when you made the size of the cilia large?
It doesn't matter from the ion inside the cell because everything remains more or less constant. But of course, you have different driving forces for potassium, so you have to account for this and some stuff. So it does matter, and it does matter because, as I said, that in this case, the chloride flows from out. If it's depolarizing, it flows out of the cell. And so basically, if you change something outside, this is much more robust than if you would have a sodium current that flows in. Because then if you change something, like usually if you have cells that are in a controlled environment, it might not be that different. But if you have some, like the olfactory neurons that are in the nose where the environment can change, then it makes a big difference to replace the sodium influx by a chloride outflux.
Okay, maybe a last question. So after everything has been integrated or past this little cilia, and they go into these more bulk type compartments, what happened to the signal?
That's a good question. I think this is something that comes next. So basically you have now to see how this current drives action potential generation. So this is what would be a nice project now, to see how this current now is transformed into action potential, you know, by cell body depolarization and whatever this kind of thing, to couple this a model with action potentials. This is one of the next steps that we hopefully will be done somewhere.
Okay. Okay, so let's close now this fourth week of workshop dedicated to computational biology. This week was quite interesting in terms of the modeling and the simulation associated to neuronal cells, specifically of dendritic spine, sensory cells, pre- and post-synaptic terminals. And to conclude, I would like to thank all of you for being here and for your participation in this meeting. Thank you. Okay.